Good morning, everybody. Everybody have a good weekend. Yeah. Good. Chilly one to start this week. So we don't quite have everybody in here yet, but week 2 we're going to be switching to different parts of the bridges. We're going to start with the deck. I think it's called superstructure, concrete replacement for superstructure, but essentially this is going to concentrate on the deck. And obviously that's a big, huge part of what we do. So we're going to start out the week that way. We're also going to hear about concrete issues from Jacob Dave from the concrete office. But before I really get into the rest of the week, the last I heard from the Tech Cert office is 10 of you had completed the test. There was a few more that were working on it, so I don't have the latest update, but as of the original, there was 87% was the average. There was 5 in the 90s, 4 in the 80s, and there's 1 in the 70s. I don't know if anybody's still left to take it. I'll get more results later. But I know one of the comments, and I did just send a comment on to the Tech Cert office, is you guys would like to just have the ability to review the questions that you had wrong on the test. So is that kind of common? Everybody like to see that on? Yeah. So we'll see, even if for the week 2 they can, if that's something they can turn on and give the opportunity to do that. So I don't know, there might still be somebody that's still left to take it, so, and we typically don't go over the exam. 5 years ago we used to. When it was a paper exam in class, I used to spend this time going over the ones, especially that the more people had tended to get wrong, but we don't have that opportunity anymore, and the Tech Cert has kind of told us to don't do this. At any rate, yeah, I think the main reason is they just want to make sure that the tests stay pure, that people aren't jotting down notes. But how still, you guys, it's no different now. If you get one wrong, it could be one that somebody could write it down, they can take a picture. It's up to you guys for the honesty. But anyway, that's one of the things that has come up in the past.
It just feels weird. If you got something wrong, are we supposed to know these things?
We're supposed to, exactly. And that's why, for us, the Mentimeter is a good way. It's kind of a way to review the concepts and not exact wording verbatim, but it's a way to get the concepts and do it in the class setting. But at any rate, I have asked the question, and hopefully, maybe we'll see for the week 2 exam. It's something it's a topic switch or something. Some of you had said that other exams you're able to do that. So if you're able on other exams, I would think it'd be something we can just turn something on. That being said, any other questions or observations on the exam that you want to bring up? The questions seem fair?
There were a couple of questionable ones.
A couple of questionable ones?
Yeah, it seemed like there was a few that had multiple correct answers, but you can only select one. So
Okay.
like pick the best answers, take a shot in the dark.
Okay. So we'll look at them, and like I said before, every test we see what the distribution was. So out of 33 students, if half of you got something wrong, there's probably something wrong with either the question or the answer or the way it was worded, something. And so we will tweak that. This year, for this week 1 test, I had corrected 3 questions. There was 3 questions that in last year's, too many people were getting the wrong answer. And that's not necessarily because people are just totally spacing it out or sleeping during class. It's often because the question or the potential answers are wrong. So we'll look at that if there's some that are turning out that, yeah, it's just a misleading question. We'll try to. Any other comments, questions? Okay, one other thing, Holly was so kind as to bring in a couple of buckets of cookies back there, so thanks, Holly, for doing that. So the back table, feel free to help yourself at break or now if you really need a sugar fix early in the morning. So appreciate that. And I guess the only other thing before we start into session 12 is to talk about our classes. So again, we will start at 8 the rest of the days, Tuesday, Wednesday, Thursday, Friday. Today, as I mentioned, it's mainly deck. It's called Superstructure, but it's mainly the deck. And casting, curing, placement, all things deck will be handled today. We're going to try to get to a deck placement video. It's on the MnDOT webpage, but it's a pretty good way to put it into a video of the things we're trying to learn instead of just doing things on the PowerPoint. Tomorrow we're going to have a session on barriers and railings. We're going to have utilities, we're going to have a wearing course, and then we're going to have special structures. So those of you who have more of the box culvert type of bridges, there is a portion that will be box culverts, and then also we'll do some retaining walls and MSC walls, things like that. So that'll be Tuesday. Wednesday we have Kevin Casabud from OCIC coming in, talking about contractual stuff and how we deal with contractors. Kevin's pretty good. I'm sure some of you have worked with Kevin over the years. And so he'll be in, and we'll also then have coach panels. And much of the day Wednesday, Paul Pilarski and myself kind of tag team on a reconstruction. So it's not all new bridges. There's a lot of bridge rehabs, so we'll do that. And Thursday, we'll get into a little thing on quantities. We got some environmental stuff with regulated material. And then environmental, Dwayne Stenlin in the afternoon. Deck fittings and slow protection. So Dwayne's always a highlight, we know that. So many of you have had.
You know when he's in the building.
Yeah. Yeah. And so Dwayne is passionate, and you guys are pretty fortunate. You're the second, I believe you're going to be the second of the last bridge class that Dwayne will ever present to, because he's going to retire, as I'm going to retire. So, anyway, we get the pleasure, and his last class will be my last one as well, in the first week of March. And then we'll have a session on project safety, and then Andy's going to come back in with resources and things that we have that, on the website that we can. So, Thursday morning. Yeah, slot for makeup. What we have always tried to do is, I hate to overrun on Friday, so I put a session here just in case, but what that most likely will be is a plan reading Mentimeter. If it's still open, it's going to be a plan reading Mentimeter. And so that's what, Thursday morning. So we'll get that. Over the years, I've really found that the best thing for you guys as bridge inspectors is to be able to familiarize yourself with the plan, and those Mentimeter plan readings have been pretty good. So that's where we're sitting now. So that's the plan. The plan again is be done at 4:30 every day. I know one of the comments, and again, thanks for your comments on the review. One of the comments was get done at 4, so they don't have to battle that traffic so much.
Oh, it's so bad.
But anyway, we are set to be done by 4:30, and I aim to be done for sure by 4:30 every day. Some days we'll be a little earlier than that. Okay, any questions before we dive into session 12? All right, well, we'll talk about concrete placement for superstructures. And in here, we're going to be talking largely about 2401 concrete bridge construction. And that's going to talk about placement of rebar, where you tie stuff. It's going to talk about placement of concrete, how you place it. We'll talk about curing of concrete, how you cure it. There are some references to the structural concrete 2461 and metal reinforcement, which we learned about already last week. We have seen this slide before, but just a reminder of the north region, the regional engineers. So Nick Hultvick is now coming to the end of his time there. Kyle Fritz, who we haven't met, is going to be taking over the north region. Carl Grunwald is the south region. And Pratik Patel is going to be here, I believe, tomorrow, and he is the Metro regional construction engineer. So, again, feel free to reach out to those folks with any questions. Again, even if you're county, if you're city, if you're consultant, they are a great resource. So we'll be looking at the bridge deck video, as I mentioned. We'll look at what's called stool height elevation or stool elevations. We'll go through some numbers of how do we, the beams are cambered. We learned about beams last week. And if beams are cambered, how are we going to make the deck be uniform and straight after deflections come out? So we'll be talking about how to do that. There's some conversion. There's a little chart. We'll see it on slide 77 of feet to inches, skewed bridges, overhang deflection. And some of these things are in the bridge construction manual. So to talk about superstructure, the superstructure is what part of the bridge, lower or the upper? Upper part is the superstructure. So it's going to include the deck, it's going to include the beams, it's going to include the barriers. It's that upper portion that essentially it is containing the vehicles. And it transfers the loads to the substructure. So the substructures then are the abutments and the piers, the footings, the piling, all the loads that then come from a truck that's on the deck, gets itself into the beams, gets itself through the bearings down into the ground. And so again, the superstructure, we studied this last week. It includes the beams and the girders, the deck slabs, barriers, sidewalk. And essentially, we are only going to be talking about concrete placement for the superstructure. Throughout this presentation, I put the page numbers on our BCI course manual, so if you are at all interested, even in the future, that's where you can find it in the course manual. So typical bridge with beams looks like this, and the superstructure is the part that's shaded there. So the deck, the beams, and the way the load gets transferred. A slab span, this kind of a review, it does not have separate beams, but the slab, or we might say the deck, is thicker. And oftentimes their spans are going to be 30 to 40 feet, sometimes as much as 60, and you increase the depth of that concrete, put a little more reinforcement in there, maybe some post-tensioning to get that. Every time we have a superstructure, there's got to be a way to distribute the load down to the substructures. Oftentimes it is through bearings. And this is a depiction that would show at the abutment there's an expansion bearing, meaning that the beams would sit on a bearing, and as temperature expands, contracts, that the load will sit on the bearing, but the bearing will enable it to move. If we didn't, if we locked it up, there could be some issues, unless, of course, we had an integral abutment right here, single line of piling, and then that abutment could move. So again, showing what the superstructure is. So in our spec book, the very first part of 2401, and maybe we just open our spec books because we may wonder, why are we going through something like this? So the very first part of 2401 on page 336 of our spec book talks about the term bridge slab for the structural portion of the deck. And so and the bridge slab is on the very top of page 337. On the very bottom of page 336, there's a bridge deck slab, and it says complete structural slab and wearing course constructed monolithic. And then there's a bridge structural slab, and it says a structural unit upon which will be constructed a separately cast concrete walls. The reason for this definition is there are some differences in how we cure and how we place the concrete. If it's a full riding surface, if it's monolithic, meaning we don't have a separate wearing surface, we have to be spot on when we're casting that deck, because we don't want the traffic to have to be, bumping all over. And so the definition, and there'll be some more slides that will explain this a little bit more, but essentially the bridge deck or the bridge slab, as is in the terminology in 2401, it's this portion, it's the structural portion of the deck where the vehicles are riding. So the deck then is the direct support for vehicles and pedestrian traffic. It can be a reinforced slab, it can be timber, it can be steel plate or grating. By far, the biggest that we use in Minnesota is the reinforced concrete slab. Very, very typical. But there are timber bridges that have a timber deck. There are some steel plate ones as well. But the purpose then for a deck is a couple-fold. One is to give traction, and if you smooth it out like your basement floor, or like you see in the warehouse floors at Home Depot or something, if traffic was on that and you get a little bit of snow like we had out here, extremely slippery. And so we want to have enough traction. And we'll study about this, and there's a couple ways to do it, either through tying or through grinding the deck. And that's one purpose. The second is to transfer load to the other supporting members. So we have a deck that is spanning 8 feet between girders, so you've got a wheel right in the middle. That load has to go 4 feet to this beam or 4 feet to this beam. And so the deck has to be reinforced to be able to transfer that load. And so it conveys that load to a system of beams and strings. So let's look at the definition. So we opened our spec book already to 336. And so it's written here. So bridge deck slab, the first one that's underlined. A complete structural slab and wearing course constructed monolithically. Monolithic means it's all one piece. There's not a separate plane. So that's a bridge deck slab. Bridge structural slab then is a structural unit, and there will be a separately cast concrete wearing course. So we see the difference. Monolithic, and typically if we just use our typical dimensions, a monolithic here would be 9 inches thick. The structural unit is typically 7 inches, and then we'd have a 2-inch wearing course. It's not always 7. Depending on the beam spacing, it might be 7.5, might even be 8. But typically 7 inches is what we see. And then just to further confuse everything, there's a definition for bridge slab can be either a bridge deck slab or a bridge structural slab. And again, as we get specifically into the curing and into the finishing and the tolerances, is it going to be an 1/8 inch in 10? Is it going to be a 1/4 inch in 10? It's dependent on what our definitions are here. Highlight a couple of things here. Okay, so to put it a different way, so a bridge slab, again, can be either, but a bridge structural slab is a reinforced slab under a separate concrete wearing course. And then the concrete wearing course is typically 2 inches to give you a total thickness of, in our typical case, 9 inches. But a monolithic slab, it can be called a bridge deck slab, or again, it can be a bridge slab. So it's a little confusing, especially here the first time we see this, but we'll keep it in mind. So when we go over it, well, it looks like I have the slide maybe a little out of order. Next time we'll go up to this one, because then the bridge slab is the bridge structural slab. The reinforced concrete slab under the separate wearing course. So that one probably should have followed the previous. But again, we're going to talk about stool heights, we're going to talk about layouts, we're going to talk about rebar placement. We're going to talk about what the computer programs are to enable us to cast a deck. So after all the deflections are out, we have a smooth deck surface. We talk a little bit about what do you do as an inspector, pre-placement, the strike-off rails, the screen strike-off rails, placement, texturing, curing and protective oil treatments, if any. So again, page 12.1 in our BCIC manual. So pictorially, all I had up there was words before. So bridge slab now, pictorially would be like this. What's highlighted here in the red is the bridge structural slab. So then we can see the little crosshatch piece that's up above it. That's the 2-inch wearing course. Those dimensions, obviously, they might change, but typically it's bridge structural slab is 7 inches and a 2-inch wearing course. The bridge structural slab. A monolithic would look like this. A monolithic deck is going to be full thickness. We still are going to want 3 inches of cover to our deck rebar, but there's no separate wearing course. Very common nowadays on bridges. If we can do a monolithic, we do them monolithic. If there's weird geometrics, then we'll oftentimes use the low slump overlay. But just to point out, so we have 3 inches clearance here. I'm going to go back to the previous slide. Again, we have 3-inch clearance. But in that case, the 3-inch clearance includes the 2 inches of the low slump, plus then it's going to be 1 inch of the top of the structural slab to the rebar. The way we make a smooth grade on the bridge, even though the beams are cambered and they're going to deflect, is we use what's called stool heights. And the stool heights are meant to be a variable distance depending on where you are on the beam, how much camber there is, and how much deflection is expected at that particular point. And so we'll be talking about that a bit more. So it has a couple different terminologies. I use the term beam stool, also called a stool height, sometimes it's called a haunch. And again, it's that variable thickness. It is constructed out of concrete, it's cast the same time as the deck. And we'll see some pictures that will show how to do that. So the purpose is to provide uniform deck thickness conforming to the profile grade of the bridge, and then also to make a smooth riding surface. We don't want a bunch of waves and whatnot as you're going across the bridge. We want everything to be smooth. So we've talked about a couple of these. The camber is something that is either built into the beam, like a steel beam is fabricated in, or a pre-stressed beam. It's the camber comes in because of how the pre-tensioning is completed. The deflection is then you have a camber and a beam, and you load it with a concrete deck or live load, and that beam will sag a little bit. So that's called a deflection. And so the deflection is the downward movement of the beam due to the loads applied. Residual camber is what's left after all of those things happen. So a couple of pictures here. So the beam camber, you have a beam that comes out like this, and this is real typical. You can, just with our eye, we can see what the camber is. And if you take a string line and you go from end of beam to end of beam, this is our camber. So we can measure that. We can say, okay, that looks like it's 4 inches. After we cast the deck, some of that will come out. As we can imagine, anytime we put a load on anything, it's going to take some of that camber out through deflection. So deflection is going to happen, and so in essence, we want to be able to, as we're casting this, we start a little bit high, knowing that it'll come down some, and at the end of the day, we're going to have a nice smooth grade across that bridge. So residual camber is something that gives the appearance that the bridge is strong. If we had a negative camber, if this thing was actually bowing down, does that mean the bridge is going to fail immediately? No, it won't fail immediately, but it looks bad. So to the public, they might look and say, that beam it looks like it's going to fall down. And so it looks much more stable if we have some positive camber, positive residual camber. And so that's what we're looking at. Even though saying it looks like a bridge is collapsing or overstressed, it would not be, and we can't say it's not, because it's possible that maybe over time some of those strands have broken or whatever. So safety inspection would certainly be looking for that, but just because there might be negative camber doesn't mean that it's going to fail. So this is what a typical cross section might look like. So in this case, we have a 44-foot wide bridge out to out, the roadway 40-foot 10. We got some lanes on there, and we have 6 different beams. And the beams are set at different elevations controlled by the cross slope. So in this case, from the center line, what is the cross slope either way from, if this is the center line at this dash line? 0.015. Are they going both going in the same direction? Opposite. So they're going down. So the high point of our road is right here, because then from this point it goes down 0.015 to the right, and to the left of the center line it's going down 0.15 feet per foot to the left. So based on that, we have different geometrics. Also then, going in and out of the page, we're going to have a profile grade. Is it going up at a 3% grade? Is it doing a curve right over the bridge? What is the roadway doing? And so all of those things have to work together. So this slide is also saying the differences in elevation of the end of the girders is accommodated by the elevation of the beam seats at the abutments and the piers. And so here is just an example of a bridge that we can see that, you know, this one, that little pedestal height is maybe 3 inches, this one's maybe 6, this one's maybe 8 or something, whatever the numbers are. But that's all based on where these beams are in relation to what is the cross slope. With the intention that we never have too high of stools or we don't have too short of stool. So we'll get into that a little bit more. Okay, so from our plans, what are the cross slopes on either side of the center line of southbound CASA 4 on our bridge? And what direction does the slope fall in? We got our plans. And we're looking for southbound CASA 4. Either side, which, what do we have there for our cross slopes? Who's got a number to give them?
Over 7.5%,
What was that?
2% or 1.5%?
2% or 1.5%. So yeah, so there's a 0.015 and there's 0.02. So that means it's, you know, 0.015 feet per foot. What page do you find that on, David?
1A.
So 1A has it. There's going to be other places as well, but 1A is a good place. Okay, everybody find center line of CASA southbound, CASA 4 southbound. Everybody find these numbers. Are they going in opposite directions or they're both going in the same direction? Same direction. So they're both going down to the left. Okay, everybody able to find that? Okay, so here's where we are. So 1A. So right here, 0.015, and you get to the center line and it changes to 0.02. And so each bridge is going to be a little bit different, but each bridge is going to have similar things like that. There will be cross slopes. Most likely there's going to be more than one. Sometimes, you know, they might, on a narrower bridge, maybe it's from a center line, it's just 0.02 everything, 0.02 everything. But oftentimes the shoulder area gets a little steeper. Anybody know why that would get just a little bit more grade?
Get rid of the water faster.
Get rid of the water faster, and it's faster, that's correct, and it also gives a little more area so that whatever water is coming in that gutter doesn't get into the roadway. So hydraulics engineers figure that out of how wide does my shoulder have to be so that I don't encroach into the roadway. So they, I don't know, whatever they use, 5-year flood or a rain event or 2-year, I'm not sure what numbers they use, but try to keep it there, but yeah. Okay, so that's what happens there, so everything is falling down to the left. So that matters when we are designing and calculating our stool heights. So here's another picture. So at the end of the day, we want to have a profile grade that is nice and smooth. So everybody who's driving across isn't doing the bumpy bump coming across the piers. We can see from this little diagram, as bad as it is that there's probably going to be a higher stool elevation here from the top of the girder to the profile grade as there is at the center. And so, you know, scales are greatly exaggerated. Things don't look like this. When we look at it, say one of the spans, it might look something like this. That we have a girder that has a camber in it. We have a profile grade that at the end of the day it wants to remain nice and constant. But we also know that if we would start pouring our concrete at this line, we're going to get deflection. And so if we didn't accommodate the deflection, we would end up with a roadway that has a dip in the center of that span. So we're trying to accommodate all of that. But the varying vertical distance between the top of girder and bottom of slab is called the stool height. And we'll be talking a little bit about that. So here's another little depiction of what the stool height is. So what do we do to calculate stool heights? So the engineer or the people that put together the plan, they can figure out what is the final elevation of the deck at points along each girder. And at each point, we need to add in the anticipated dead load deflection due to the weight of the slab, due to the wearing course, if there is any, due to the railing. And this is also in multiple steps because the weight of the slab in this case is essentially taken only by the girder itself. But once the slab is cast, that actually has like a T shape. And a T shape is going to be a little bit stronger and deflects less than the girder itself. And so all of these things matter as to when they're applied. So the weight of the slab is only on the girder. The rest of these will be on a composite. So you have the slab acting like a T on top of the girder. And so then the engineer will also provide the stool height elevations by subtracting the thickness of the slab and wearing course to get a predicted bottom of deck elevation at each given station. So we're going to be seeing this term vertical increment plus dead load deflection here in a few slides. So what do you as the inspector or what does the contractor have to do? They need to calculate the stool height based on the predicted bottom of deck elevation minus the surveyed elevation of the top of the girder. So now we see we're out here in the field and we're actually surveying the top of girder to get where is that girder right now, where do I think it is compared to what the bottom of deck should be before we cast our slab. Now the normal stool heights range from 1 inch to 4 inches, and then all false work systems need to be adjustable. So I had that board hanger up here, we were talking about forming false work. That's how we make that variable system work. So that is something that we've done. Here's a picture of what that looks like. So the board hangers are right here at the edge. You see how they're just kind of fastened over the top flange of the boom. There is some type of a little kicker here to keep it from rotating out. We see then a stringer. So this looks pretty deep, probably like a 2x10 or so. And based on the spacing between our beams, this might be a 2x6, might be a 2x8, 2x10. It might be, some of the LVL type lumber even, depending what the contractor wants to use. Another thing they're going to want to always do is make sure these can't move, so they put a little shim right in here to tighten everything up. But that's a real typical system that we have. The other thing we see then is a little paint mark right here, and then 5 feet ahead there's another paint mark. And this one there's a paint mark, there's a paint mark. As we learn here about stool heights, this is that center line of bearing, this first one. And so either the contractor or sometimes it's the inspector, but nowadays our specs are relying on the contractor to take this. They'll go out there and they'll take the actual elevation. What is the elevation at this orange mark? What's the elevation at this orange mark? So what do you as the inspector need to do to determine the actual stool height? First is request the deck elevations or bridge construction elevations from the bridge designer or the engineer of record through the project engineer. And the bridge construction elevations are forming elevations that account for the anticipated deflection and all of the geometry, all of the profile grade, the cross slopes, everything like that. Don't wait till the last minute. Make sure you have that and request it in advance so that you can crunch the numbers and be ready. Just a note here, the actual stool concrete volume has a little effect. It might be a forming issue. The plans in the past used to put a volume, an estimated volume on that, but the contractors seem to take advantage of that as they do a lot of things. And so that's no longer on the plans. So then, now you have those construction elevations, now what do you do? So the contractor, the surveyor, inspector surveys the top of the girders at predetermined locations, normally 5-foot intervals. But it will always start then at center line of bearing at the abutment to the center line of bearing of the abutment. It goes on every 5 feet. The survey elevations need to correspond with the computer output. And sometimes the engineer record will calculate the stool height and give it, if they give the station and top of girder elevation. So depending how the process works, but the same thing holds, is there's a computer output, the stool actual elevations need to be input, and then somebody will calculate the stool elevations. So what do we need to have to develop the bridge construction elevations? You need to know the vertical and the horizontal alignment. You need to know, is this profile grade going up straight? Does it have a curve on it? Whatever. You also need to know horizontal, those transverse slopes that we looked at. Working lines. What's the offset from the working line to a particular point on the beam? Because if you're at an 0.2 slope and you're 9 feet away, it'd be 0.018 difference in slope. But if you're 15 feet away, it'd be 0.03 from whatever your center line elevation is. So, you need the station, essentially you need the station and offset, and then know the cross slopes to what you have. You need to know lane widths and slopes, the deflections, beginning and ending stations, and then any span information. Where are you, especially when we talk about deflections? Are you right at a bearing where there's no deflection, or are you halfway out the beam where there's maximum deflection? So from our plan sheet, we have here, there's a lot of information that's on our plan sheet. All of the vertical information, so if we would look at our, it's hard to tell here, but we've got all of our curve information. So there's a PVI, point of vertical intersection, gives some stations, gives the grade to the left, grade to the right, and then BBC back over here, different things like that. The general plan then would have the different lane locations, the location of the median, things like that are all shown here. And then, of course, our framing plan. So now what we're going to want is to have elevations at each one of our beams from center line of bearing 5 feet out on every single one. And so the person that's putting together the construction elevations or the beam elevations needs to put all of this stuff together in the program. So you might ask for, okay, we are going to want to know all these different things. Obviously, we need to know at each girder, because we want to set the stool height for that. But we also are going to want to set our barrier. So, maybe you can give us some elevations of the barrier. Maybe you can give us the edge of slab, center line and profile. All these things can be requested. That what should the elevation be? And then you as the inspector should also be asking the contractor, is there anything you want for your operation? Where do you run your screed rails, for instance? And all of those kind of things. So a lot of information can be given. So here's another, it looks like a little pedestrian bridge. Again, you could say, I need elevations for each of the beams. I want the edges of the slab, both the bottom and top of the edge of slab. I want profile grade, I want gutter line, things like that can be requested for each one. Okay, here is what a bridge construction elevation looks like. A lot of these have stayed the same. Nowadays, there's a lot that are on Excel spreadsheets. Who in here has done construction elevations on a bridge? Is anybody? Oh, there's a few, good. Okay, so there's a few you've used something similar to this. It's not, maybe won't be exactly, but again, it might be an Excel spreadsheet, it might be other things. But the things that we want to have, there's going to be a column that somehow is going to say this: the vertical increment plus dead load deflection. That what is our vertical elevation plus, like say right at this location, say I estimate my dead load deflection is going to be an inch. We would want to have end of day plus 1 inch is what I want. So my profile grade plus 1 inch should be what this number is. Okay, so then that's going to vary obviously by each station, as well as then what is the offset. So in this case, the offset from center line of survey was 4 feet. Gets to the left, we have X and Y coordinates, we have elevation of top of slab. At the end, plus then the dead load deflection number that is going to come in here. And this is actually at bottom of slab. So you can see top of slab, this number is a little bit lower, so it's already deducting off the thickness of the slab. So there's a distance from the center line of bearing, there's the elevation, and expected deflection at bottom of slab.
There's a reason on that example why they started and stopped 9 inches from the bearing? Oh, I see, I got it.
Typically, the end of beam will go about 9 inches, but if you're really astute, and we're going to show this, there is actually an error in this sheet. Yeah.
I just noticed, haven't realized afterwards I asked that question, that they got center line up here, and then center line bearing.
Yep.
Center line bearing.
Yeah. So, I'll point it out right here, then we'll explain a little bit further. This column says distance from center line of bearing.
Yeah.
This shows 0 at center line of pier.
Right.
The center line of bearing is 0.75. That should be 0. I've kept this in here just to point this out, that just because somebody, especially us engineers, gave you that, don't count that it's right.
So if you had that situation, would your center line of structure then be minus 0.75?
Yeah.
Okay.
Yep. Yep, it would. So yeah, this would be minus 0.75, this would be 0, and then this station would change so that it's 5 feet from center line of bearing. Because, and the reason we do that is that center line of bearing theoretically should be 0 inches of deflection. Because you have a girder sitting on a bearing that it's not going to move. As you put a load out on the beam, no matter what the beam is doing, it's balanced on the bearing. It's not moving. So, but yeah, very good observation that this number should be 0. So, actually, you could have a slide in here, and when I realized that a few years ago, I thought I'm just going to keep this in here because it's a good teaching point to say just because this came out from some engineer who thinks they know what they're doing, it isn't necessarily right. There can be errors, so be checking for those kind of things. Okay, just a couple of other oddball things, so maybe not oddball because we all want to be safe. There needs to be safety posts Because to go out and take elevations out along this beam, there's nothing to protect. You haven't put the decking yet because, we're trying to get elevations to where do we put the deck. And so you're out there walking across, in this case, it looks like it's even over traffic. And that's why I think our current specs would say, contractor, you go out there and do that. We're not putting MnDOT inspectors out in that situation. So Nick talked about, we don't weld to the top of our girders, so the plans will not show a bolt location for these kind of anchorages. The contractor has to tell the fabricator, okay, go and give me a hole every 10 feet so I can put my static posts or whatever. So here's a picture again, center line of bearing. So we want to know where the center line of bearing is compared to end of beam, and then we'll be measuring every 5 feet from that. So again, center line of bearing, because we know there's zero deflection at that location. So here's just a couple of pictures of how they're lifting up pre-stressed girders. But this essentially is saying it's difficult once we get up there in the air to be measuring 5 feet and putting a paint mark. So if you can, while these beams are on the ground on a truck, this would be the time to do it. Now, sometimes there's no time. They come in and boom, they're up in the air. But if it's sitting there and there's an opportunity to do that, mark centerline bearing and then go out and mark every 5 feet. Or if the steel's on the ground there for a while, you could do the same. So here's one where, I think this is one of those single point bridges again, but there's an awful lot of points that get marked out there. And we're going to have elevations at many different places. So mark those survey points to correspond with what the construction elevations have. Splice plates, sometimes they'll fall within that 5 foot. But it doesn't really matter, because all we're doing is we're taking an elevation to show where our bottom of deck forming is. So even if it happens to be right on a splice plate, so maybe where he's surveying here, maybe this will end up being a 3-inch stool height, and maybe this one, because it's an 1.5 inch plate, maybe this would be an 1.5 inch of stool height. So we're just measuring wherever that 5 foot comes. We don't say, oh no, I'm on a splice plate, I better go back 3 feet. Well, we wouldn't have a construction elevation from this point. So you make it wherever the 5 foot mark comes. So the typical plan note would be something like this. The contractor will take elevation to the top of beams. After erection, allow for deflection to show. So again, back in the day, this is real typical. This is an old MnDOT inspector, John Nordquist. This was on Unweave the Weave project. But this was typical process back then.
That's Don?
Yeah, Don? Yeah. Good guy. Yeah. And then, from in our plan, we'd have these dead load deflections. So essentially, that's what the kind of thing that where we're looking for. The contract will take those. Okay, we're going to run through a couple examples before we take a first break of the day. So we want to check before painting our marks what's going on. So in this case, we're looking at beam B1. We're center line of the beam. We're 4 feet off and so forth. So a distance from center line of bearing. So we've already talked about that a little bit. And it goes from one abutment all the way down to center line of bearing of the other abutment. And we can see every 5 feet, we're going to have then a corresponding vertical increment plus the dead load. Now, the stool height, we mentioned this, it's the difference between the bottom of structural deck and top of deflected girder. The location that we calculate is right at the center of the girder. So we've seen some of these girder flanges are getting to be like 3.5 feet wide, but just for easy math, what if we have a 3-foot girder and we have an O2 slope coming down here? What's the difference in expected elevation at the left side to the right side? We got 3 feet and we're an O2. Right here?
600.
600, 0.06. So 3 feet times 0.02 would be 0.06 or 600ths, or that's going to be 3/4 of an inch. So 0.083 actually is 1 inch, so we're just shy of 1 inch. So that means if we had an O2 slope coming down to the right, this elevation, this little stool height, would have to be, say, 2 3/4 inches, and then 0.06 difference, so that this would then be 2 inches difference. And so what we would have is, the number we would have is, would be 2 and, I'm lost in my mental math, 2 3/8. Thanks. Monday. 2 3/8. And this is what it looked like. So now you come out here and based on what a stool height elevation is, we can then make up an edge of deck. Okay, so this is the one where deflection is always 0 at bearing. At center line of bearing, it should be 0. So right here, center line of bearing, but they are claiming it's 0.75 feet from center line of bearing. Okay, so let's just look at these numbers. Should be only the difference of the deck. And so if we take top of slab 903.0638 minus 902.48899 would be the total deck thickness. And we do that math, it's 0.5739. Well, it's not 7 inches, which is 0.5833. This would be the perfect time to say, engineer, it looks like somebody messed up. We don't have the correct numbers here. And so go back and say, let's get this right. We're trying to build a bridge, Swiss watch, top of deck. So again, it's just things to look for as we go through. So there we see flashing in red. That is not 0 feet from centerline bearing. And so there was. So here's just a note. This is what the plan sheet, and even our plan sheet here, 27138, used to have notes that would show what the assumed stool height was. But there were some claims then disputing these informational quantities, so MnDOT no longer provides that. We let them we'll take the brunt. So contractors pushed, and finally they don't get that in. So stool heights for the forms, this is again what we look at. So it's the bottom deck form. We take the vertical increment plus dead load deflection minus the top of the beam elevation. It gives a stool height. So if we just do the math here, 800.178 minus 800 is 0.178. So that's about 2 1/8 inches. 0.17 is to be right around the 2-inch mark. And the deflection diagram, so we've looked at this before. What is the deflection? And so here the estimated dead load deflection is 2 inches that we'd be able to put into those documents. So the special provisions do talk about the elevations be taken after erection and to allow for the slab. And it also says take elevations no more than 75 calendar days prior to slab placement. So the reason for that is these concrete beams, because of the pre-stressing in there, they will continue to camber over time. And so if you took elevation, say in the fall, and you waited until spring to cast, those beams will continue to grow in camber. And so then comes spring, and now your elevations aren't going to be right anymore because maybe that camber is increased by a 1/4 inch or 3/8 inch or whatever, some number. So be aware of that in the special provisions. Be aware of all of the notes that we have. Just to look at what some of the camber is, and again, we've noticed for the different spans, we have different dead load deflections and different cambers that are anticipated. For steel, it's going to be similar, but typically steel is 1/10 of span. So they're given the deflections every 1/10 of a span. We've got a short span over here, a little bit longer span over here. They're always given at 10 points along the bridge. And so this is actually what we have from a bridge, steel bridge. So the dead load deflection there is 0.0. Okay, it's 10 o'clock. We're going to take a break, and then we're going to come back and we're going to do a little exercise of steel shot. So let's take a break until about 10:15, so about 13 minutes. And cookies in the back. Come on.
We could use the refrigerator.
Yeah.
Figured something to do.
What was the
Good question. But it's nice, it's just like metric. Engineer scale and metric.
I want to chop that out.
And then I come back on here,
Okay, we'll get rolling here again on stool heights. I'm going to send around the daily sign up a sheet here, so we're on the second week. So you start putting an X in the right box. Any questions about what we went over in the first 45 minutes?
I don't know where they are.
Okay, so we're going to actually do a couple of little number crunchings here. So if we have something that we come out to the field, we take our elevations at the girders, and we have these kind of numbers, what do we have? So we'll have a little exercise here. So the thing we always want to make sure is, are we in the right place? So B1 is beam line 1. And so, we look at that, and so the beam 1 is right up here. So anytime we're doing any of this, what do we have? Are we the right thing? Are we in the right span? Is the line bearing pier 2 to abutment 2? So, we just want to make sure everything is right. So, here's some numbers to crunch. So, from what we've said so far, we have a station, we have a vertical increment with dead load, we have an elevation. What is our calculated stool height in feet for this number right here? So the vertical incrementless dead load deflection is where the bottom of the slab wants to be. The elevation on top of girder is where the girder actually is. So we're figuring out the stool height. Who wants to tell me what that number is? 0.12. Everybody see how to get that? So we're just taking 1250.44 minus 1250.32, we get 0.12. So we can present it that way, or we can present it in inches. What is 0.12 in inches? What's 1 inch? Anybody know what 1 inch is? 800, 0.08, 0.03 actually, 0.08. So we're a little bit more than 1 inch. So 0.12 is how much? It's about 1.5 inches. So this might be the number that we would then paint on the girder for that particular location, at whatever station, however far we are past, whatever. That's we have 1.5 inches as the stool. Okay, what's our next one?
10th.
So who has the numbers on this side? 10 hundredths. Way over here, disagree?
No.
No disagreement? Okay, so we're 0.44 minus 0.34. We see that these have all kinds of significant digits. I think the carpenters can get down to the 8 and 10 thousandths? Probably not. So typically we would just round to the nearest hundred, which would be an 8. So they're not going to be able to set their forms tighter than an 8. Okay, so that's 0.10. What's that in inches? 1 1/4 about. So if 0.08, and for every 1/8 inch we're going up another 0.01. So 0.08 would be an inch, and plus another 2/8 or 1/4, so 1 inch and 1/4. How about the next one? Now we got a problem. Do we have negative 0.01? 0.4, here we can round up. 0.44 minus 0.450, negative 0.01. What's that mean?
Somebody didn't calculate something right.
Not necessarily.
Well,
So it's a negative 1/8 inch. It's called a negative stool. We'll talk about this a little bit. And you can still do this. It's just that your forming becomes a little bit more complicated. So this, it's not necessarily something's messed up, it's just that the way that girder is compared to the profile grade, compared to the cross slope, compared to where you are on the girder, all that stuff said, well, we have a negative stool. If this is the only place we have negative stool on the bridge, we'd probably live with it. But if we have negative stool on 50% of it, we'd start to say, this isn't gonna work. Let's raise the grade on the bridge.
so how do they actually form that then?
So I'll have a couple slides where we'll talk about that. But you actually have to notch around where the board hangers sit. You actually have to notch the plywood, so and it becomes harder to remove everything, and it's much more problematic. Okay, how about the next one? 0.15, 0.15. Everybody get that one? Everybody see what we're doing for math? Anybody not see how we're doing that for math? Okay, so we have 0.15, what is that in inches? Just shy of 2, so it's going to be around 1 3/4 inches. Okay, so this would be where we're setting at these particular stations for this particular, whatever the beam is, we don't even have it on here. For those stations for that beam, I guess it's from the previous one, that's what we would have. So there is this handy dandy little chart that if moving from decimals, 0.07 to inches, you can use this little chart. So if we have, okay, if we have 0.44 as our stool, we would then go and we'd see it's 5 inches and a quarter, so 5 inches down the column plus another quarter, so we'd have a 5 1/4 would be our stool. So otherwise you can commit these to memory and you can just think about how about 0.08 is about 1 inch, and that would be how we would do it. So again, we see for 1 inch and 0.8, it's 0.08, 0.17 for 2 inches, and 0.25 for 3, and you can kind of commit these to memory, and again, that's not important for, we just need to know how to do it. Okay, so at the end of the day, this is the sheet we had up earlier, except now these are filled in. So if we would do all the math for all those sheets, so here's that -1, and some of the other guys, so we would see what we have in decimals of a foot or in inches. Okay, so let's look a little closer then at some of the things, including negative stools here, and how we set it. So this is how we do it. We have a paint mark out in the field. We have some kind of an identification point so that everybody knows what we're talking about. And then we would have some numbers that are written on here. So in this case, I'm not sure if everybody can see that, but there's, it looks like 1 3/4 inches. So the calculated stool height is 1 3/4 inches at the center of beam. So again, what's our cross slope? We might have to have a different height on the right as we do on the left. So again, the point here, they're just actually written right on it. So somehow we got to transfer the information and make sure that we're right. So composite deck construction, I guess we got a couple of pictures in here to also show what we have. So along with our stool height, we also have stagger bars over the pier, but everything makes it composite. But essentially composites construction is tying together the slab with the girder. And so there's ways we do that with shear stirrups and reinforcement and things like that. So here's just a depiction. On steel girders, we'll have these little shear studs that get welded to the top of the beams and they go up into the deck. On pre-stressed girders, there's actually some hoop reinforcement bars that come up, and that will provide a composite action. The spec book requires that the composite action, that these hooks or shear studs are at least 2 inches taller than the stool. And typically we have a 1 inch bottom clearance, and then you'll have a bar. So you got to have from your bottom of the deck to bar is 1 inch. Plus you have 1 bar transverse, 1 bar running longitudinally. And to get 2 inches, you're actually up to at least the top of that bottom set of bars. So here's what the composite action with the shear studs on steel looks like. So Nick had shown a little bit that how we fabricate those, clean them off. There's an automated procedure to weld those on. Here's a picture of the concrete. So again, stirrups that are coming out looking like that. And because of safety, they don't we no longer put shear studs in place before the decking. So when I started a long, long time ago, I remember walking beams and the shear studs were on there, and you know, you gotta kind of walk sideways and careful your pant legs don't get caught up in there. So this is a good move, it's a lot safer. Still obviously have to be careful if there's no decking, but the shear studs now get put on after the fact. So that's something that is in the specification. So it was a tripping hazard. You had to be careful walking and so forth. So once our forming's in place, if the stud height is less than the stool height plus 2 inches, longer studs need to be ordered, or I think Nick had showed a picture of, you know, they do make little stubby ones that if this was too short, you could add a little 3-inch stud welded on top, and you know, that would be a way to just increase it instead of getting full long studs. Here's a picture of some deck forming, some temporary wind bracing is shown there. So adjustable board hangers or joist hangers. Picture shown here, again with the kicker against the web, just to make sure they don't rock themselves out. Okay, so we had looked at this situation before when these kicked out. So what did we learn? We learned that you need to have something to keep those board hangers from kicking out. We learned that you need to put some kind of a wedge or a shim. So kind of between the stringer and the edge of the girder, put a little shim in there to make sure that there's no wiggle. So that kicker is important to make sure that things all stay stable. Otherwise, this can happen. So these beams, so our M series and MN series, we're starting to get thinner flanges. So the older shapes had like a 6-inch thick. Now these are 3 5/16. But anyway, it's a lot thinner a flange there. There's a requirement now for future redecking that we put a bond breaker for a few inches on each edge of the beam for the full length. And so when we come to redeck, and the reason that we started specifying this is I was on a few redeck projects with pre-stressed beams, and there's enough composite action that all this deck concrete was composite constructed. It's really hard to remove the deck. And so a lot of these edges of beams would get destroyed. And so now we're putting a bond breaker in there, so if there is a redeck, at least that portion of the deck will come off easily, and then you have a little more substance, a little more meat here, so that if you get a little damage, it's not going to...
Doesn't that kind of defeat the purpose of tying the girders to the deck?
No, because there's still a big composite zone, so you know, say we take 6 inches off here and 6 inches off here, you still have 1 foot 10. That would be composite. Yeah, so it's not across the whole thing. The specifications now require any inserts to be coated with a zinc-rich primer, and then this spec 2401 3F3C4, any supports left in the deck shall be epoxy coated or galvanized. So this one is with the pre-stressed beams, 2405. This one's with the concrete bridge construction. Okay, so looking a little bit more, so here we have a 4.5-inch stool or 4.25-inch stool at such and such a point. We see the adjustable hangers, we see the little shims that are driven in there, wedged in there to help make sure everything is is tight. And then the typical stool, again, it's going to vary based on cross slope. Let's say it's 4 3/4, that's what it would be at the center of the girder. We also see things like tin right here. So there's a little gap between the ends of girders. If we didn't put something there, the concrete would just fall right through. And so we want to make sure that that is filled up. Okay, so negative stool height. So we had, in our case, just like a negative 0.01, negative 1/8. So this shows what happens. So if we had more, say we had a negative 2 inches or something, this is what it looked like. And what are the problems that we could have? So there's a couple issues. One, the structural deck thickness is less than required. So right here at the end of the girder, so instead of a 7-inch or a 9-inch, we'd only have, say, 5 or maybe 7, depending what the total deck thickness is. So we'd see that that is a problem. Now our rebar would, instead of being down here, the rebar would come up and over. So, and secondly, then there's constructability problems with form removal. So we don't like negative stool heights. So here's a picture of what happens. So negative stool height, so the form is actually below the top of the girder. So we'd have to notch out our forming plywood. But we can imagine how all the concrete, when it gets cast, it can start to be, it'd be hard to remove the forms, hard to remove the board hangers and things like that. So that's things we want. Okay, so what can we do? So Linda said, well, somebody must have screwed up. Well, it's possible somebody screwed up, and part of these are, let's check what happened. So number one, we can reshoot the beams, gather the stool height data again, make sure everything is right. Did we shoot beam B1? Or did those elevations that got put on form for B1, was that actually for B2? And so we want to check that before we start, the sky is falling. We can also find what is the worst condition, what's the worst, the largest negative stool, and maybe fix it. But here is the thing that often happens, in the third bullet here, raise the grade, at least that dimension of the worst condition with all applicable improvements. Raising the grade isn't going to make or break the difference in that roadway. So if, say, let's say the top of our elevation is 900 at the top of our deck, and we raise it to 900.25, raise it 3 inches. All we would have to do is raise the approach panels a little bit and maybe raise the approach grading for 100 feet or something. So even if you're on, say, a redeck, you could do something like that. And just, you'd have to taper things out on the road. So this is the thing we'd have, and I don't know how many times that this was actually done in the field based on the observed stool heights. But I was involved in many, many bridges that this was done.
So do they have to go and reprint all the plans showing elevations that reflect the change, or?
No, really nothing would have to be done. All we would do is they would just make, on the stool height elevation, they would just raise everything. So if a stool height was -1 and we raised the grade 3 inches, we'd now put our stool at 2. And another stool that was 2 inches and we raised 3, now that stool would be 5. But there's no change in the plans. Nothing would have to change that.
That's something you probably want to make note of in the as-built data.
It probably would in the as-built for sure, just say that, yeah, we had to raise the grade, 3 inches or 1 inch, and oftentimes they would do it in the engineering scale, so they'd raise it a tenth. And it's easier to work with. But yeah, otherwise no need for the plan changes and things like that. But very, very common. So if that's ever a situation on your bridges don't think that, oh, no, you know, this is the first time this ever happened in the history of MnDOT. It really happens quite a bit. So an opposite thing is very tall stools. And I think Nick mentioned this a little bit, and he showed the U-shaped hat bars. I'm going to show it again. That what if we have, you know, say 8-inch stools, and these are only extending out 6 inches. Well, they're not even getting to the bottom of the deck, let alone to the bottom of the rebar. And so we would use what we call hat bars, kind of a U-shaped bar, and they would be bent in this shape, and they'd come out. Put a couple of longitudinal bars in there, and that would just help produce composite action. It would help tie all of this reinforcement and all of the concrete stools together. So that's what we have for that. Okay, so overhang concrete, placed 1 inch down on the side of the fascia pre-stressed beams on steel. It's often formed tight to the bottom of the flange. So let's, so sheet 35 of 62. Let's just look for that detail. Who can show me on sheet 35? Who can point out where that 1 inch dimension down the fascia beam is? Where do we find it on the page? Sheet 35 somewhere. What detail? Everybody find it? Sheet 35. Okay, who found it? Together. Detail F. Everybody see it on detail F? I'll put it up on the screen here. On detail F. So right kind of in the center, right? So there's a little 1 inch. Let's make it a little bit bigger. And that little 1 inch typical. So we can see there's a lot of lines here, but essentially these lines are just dimension lines. That's, you know, this top line is pointing to the top of the girder, the bottom line is pointing to where that goes down. So I see a lot of little forming details like that. So decks formed 1 inch down, and a lot of times that just gives us a little cleaner lines. Here's preparing to install the overhang brackets. I think I mentioned in the forms and false work, this is actually one of the things that many times I've gone out to bridges and the way these things have looked at how is that ever going to come back down, but they do. So the information from the form manufacturers is pretty good. False work hangers, this is an older system. We don't see this really much anymore, but always be looking at what the contractor is supplying and is there safe working loads or whatever, and make sure our calculations match. False work hangers, what if the contractor wants to use the older style that you weld right here? Allowable?
Galvanized.
Welding to the top flange of steel is not something we want to do. So we stay away from welding. What can happen is it can make a fracture, especially a transverse weld like that, and really any weld. But it can start to initiate a crack, and pretty soon, you know, you could have a fracture of that girder. So don't allow them to weld on the top. Finishing machine, the rail location, the contractor oftentimes would like to put their screed rails out here on the left, shown in blue. But we can see it's going to cause a lot of additional weight on here. And so most typically we'll end up with putting it right here. But if they use that situation, anything that gets embedded needs to be protected and coated. Anytime there is a load out here, which sometimes does happen, they should also be bracing this. So like this blue coming back shows a bracing just so that this heavy load doesn't kick that girder over. So here's a screed support on the bottom, and again, anything that remains in nowadays per our spec has to be epoxy coated or galvanized. So the overhang, the amount of dead load includes the weight of the concrete, different overhang brackets. Every manufacturer has their own info, and they will have load carrying capacity and deflection. So check to make sure that that all appears to be correct. And also then the distance from the edge of the girder matters as well. Obviously, the further you get out there, there's going to be more deflection and so forth. So you need to account for that. Well, we always want to know what's the total load carrying capacity. And it says live load and dead load must be computed. And the live load oftentimes is the weight of the workers, of the screed rails, of the screed itself, of whatever's going on like that. And this is essentially just saying if the overhang deflects a 1/4 inch when dead load is applied, it's actually raised a 1/4 inch. And the manufacturer has to supply that information. So the formed overhangs, this is a picture that, what they look like. Very, very common. Edge of deck, there should probably be one of these 4x4s at edge of deck, since there's going to be more load that's going to come right there. So the Bridge Construction Manual has more info on this, so I'm not going to get into this too much, but just showing how different configurations go. And very typically, it's this triangular shape that's very a stable type of a shape that can be used. We see deflection, little charts and stuff that happen. Potential problem area shown in red. So I mentioned that we want to have secure and stable connection. So if you have a stringer and you have a little gap and you don't fill that, as load gets applied, it can tend to shift a little bit. And so you want to always make sure of, do we have a little wedge in there, and we stabilize everything. And here's more. The Bridge Construction Manual has much more. This was a note from my old boss years ago. There was an issue that there was a failure of some formwork, and it was because they didn't engage the bolt into some insert adequately. Sometimes perhaps maybe some debris got in there, and so that's all the farther they could go. Well, I don't care if that's all the farther you can go. It's meant to engage all the way. And so this little memo just reminded, if you have any of these kind of systems, make sure that you thread that bolt all the way in, and don't just put 2 threads and say, yeah, we're probably good. Because it did cause a failure, and I'm not exactly sure what it was, but it caused enough of an issue that this went out to all of the resident engineers in all of the districts. We talked about false work requirements quite a bit last week, and the requirement again is provide false work for the overhangs, use knee bracing, cross brace, struts, ties, whatever you need to prevent any irregularities, and brace and so forth. It's critical. We want to make sure that everything is done. So this is saying if we have just a system like this, and we put a load out here, And this thing would tend to kick over the bottom of this beam because of the load that's coming down, it would tend to kick that to the right. And so, similar to what I showed a few slides ago, putting some type of a brace like that is warranted. Stringers should be under the edge of deck. Just a picture showing some of that. And again, kind of a review, but why do we check false work? Why are we learning about false work? It's so that you will be able to know and verify, is the spacing of the members that they put on there what the plans, the false work plan show. The design plans are not going to have that. What do the false work plan show? What's the condition of those members? Is the material what we need? And so we did study that. There's also a note here that all holes in the deck have to be repaired. And you caulk or put small pieces of tin over each hole. So here's just a picture of something that this isn't quite so desirable and questionable. So there's some type of a hole, and they put a whole bunch of caulking and tacked a couple of pieces of lumber or something on it. But this is more what we would typically see, some tin sealing up those holes so that, again, concrete doesn't fall. Many times it can be adjustable formwork, like we studied in the forms of false work section. So we don't need to go into much detail there. In the forms, everything has to be visually checked. And again, remember that the contractor's false work engineer has to come out if it's false work and review that this is what is required. And then if the contractor makes changes, they're certainly fine to make changes, but it needs to be approved. And make sure if there's anything that's bent, cracked, holes, knots, whatever, that somebody is aware of that. Okay, now let's get into a little bit of some of the specs. So 2401 3B7. So let's open our spec book to that. It's on page 351 of the spec. And we're going to talk about some of the particulars of deck construction. Okay, so B7, toward the bottom of the page there, says before placing reinforcement, treat the contact faces of forms of the form coating material according to 3902. Why would we do it before placing rebar? Why do we treat the forms before our rebar? The rebar would cover part of the form, kind of, but not exactly. What else?
You don't want release oil on your rebar.
You don't want release oil on your rebar. Why?
You want concrete to grab the rebar.
Yeah. So if you have a rebar and you put an oil on there, the concrete won't be able to grab on the rebar to make it composite. So that's a requirement that all forms shall have form oil applied before rebar placement. So that's right in the spec book. But what would happen if we don't put form release oil on? It'd be harder to pull the form, harder to get that plywood off. So there's also a requirement then to use water to wet the faces of forms that contact concrete. And so that's also on B-7 there. Again, all of that helps provide a way to release those forms. And also, if the forms are dry, it will suck a little bit of moisture from the concrete. And so it kind of, to put a little water there helps cure the concrete. Once the decking or the false work has been placed, including the overhang, the edge of the slab or coping line will be established by the inspector. So we just want to make sure that our deck is wide enough and so forth. So we want to check the layout. Oftentimes there's a horizontal curve, a vertical curve, there's a transition, widenings, things like that. So it's important that we establish the correct areas, the layouts, especially in those that are tapering off and so forth. So, make sure that we get that right. A contractor is responsible for a safety rail, and a working area has to be provided to finish. So that's crucial, and it's crucial that that safety rail meets OSHA requirements and OSHA standards. So there's heights, there's kick plates, all that kind of stuff, that needs to be provided. Reinforcement bars. So we discussed that in section 7, Mark did. And it's important that we have the proper clearances. Obviously the proper size, the proper spacing, and the proper clearances. Just make sure everything is correct. What's the clearance on our bridge? From the bottom of the deck to the bottom mat of rebar on 27-138. Figure out what plan sheet we're going to find it on. Just as kind of in general, where are we going to find the deck sheets and the deck rebar? Superstructure details, yeah. And so starting, is that going to be more toward what part of the plan? Starts on 35, very good. So somewhere there, we're gonna see some numbers. So who can tell me where we can find the clearance, bottom of deck to bottom mat of rebar? It's a note that hides, as much as I've done this plan, I always have to hunt a little bit to find it. Anybody starting to see what sheet maybe is beyond?
38.
38's are a good choice. So look around and see anything that's talking about clearance. Anybody finding anything yet?
1 inch,
1 inch, where are we finding it?
right in the middle, just off the left side. 1 inch, there's the bottom of the transverse.
Okay. So let's pull up, how about from the top of the deck to the top mat of rebar? 3 inches. Okay, so kind of in the middle on both, the top and the bottom details, we're able to find that. So we have a picture coming up here. Okay, so here's where it is, and it's in the, for the transverse section span 1, it's kind of just to the left of where the cross frame diaphragms are. And on the span 2, it's above the cross frame diaphragm. So everybody able to find that number? Anybody not find it? This is very common. 1 inch to the bottom is very common. 3 inches at the top is very common. In fact, I would say if it's something different, it would be a 1% of bridge type thing or something. I mean, it's just, it's almost 100%. Okay, another one. Find the clearance from the edge of deck to the top transverse deck rebar on our grid. This is going to be on a different page, I'll tell you that. The same general location.
What was the question again? Edge of deck, what?
Edge of deck to the top transverse deck rebar. So for terminology, transverse deck rebar, which way is it going in the deck? Kind of with the stationing or
Perpendicular.
perpendicular? Yeah. So it's the bars that are perpendicular. So I give you a hint on page. Look on page 35. So again, the more we look at these plans, the more we begin to become familiar with where stuff is. So now on sheet 35, anybody find which, is it a detail number? Yeah, which detail? Detail F. Okay, so for the top, it's 2 inches. How about to the bottom? 4. Okay, so it's 2 inches on sheet 35. So here's where it is. So detail F, everybody find that? So all we're saying is there is a requirement here, 2-inch clear to top transverse. And so there's a dimension that comes up here. The top transverse is 2 inches in. So among the things that we as an inspector would do is check that. So if we find that that's burning, that's, say a 1/2 inch away, what's the potential problem? If this bar, the iron workers tied it and it's a 1/2 inch from the edge.
Exposure of the rebar eventually chip off.
Yeah, it could chip off. It's closer that any chlorides that come around the edge of that deck, it's closer to the rebar. If you get a little crack there, it's going to start to deteriorate faster. So that's the reason we would say let's keep those bars some distance back. What about this 4 inches? Why don't they just make this one 2 inches? Got the slope, and you also got this little drip, V-drip right here. So if we came all the way out there, that's the same 2 inches. Where was that? V-drip. 2 inches. So your bar would be just about right where that V-drip is. I think I got a couple of array slide on that V-drip. But who could tell why would we put such a thing as this V-drip right here? So water doesn't go down the flange. So, and that's the reason. So if you get water, you get snow melt, you get whatever, it comes down this face, and water will kind of run down this slope. But this V groove, water can't go uphill, and so it would drip off right there. So simple but functional. Once the rebar is placed, we want to exercise caution that we don't keep them from, the bars from moving. Normally a wooden walkway would be provided. And here's just a reminder, no formula should be played once rebars are placed. Why? Because it would disrupt the bond of that rebar. And where bars project well above the placed concrete, we also want to brace them to make sure they stay in place during the concrete placement and the finishing. Okay, so here's from the bridge construction manual, and we'll look at the specs as well. This is actually still in millimeters, but 6 inches maximum from edge of flange to our bolsters and our chairs that are there. And then there's spacing based on the size of our rebar. And so we'll be looking at that. But this is a depiction of what goes on. We want to make sure that they stack the chairs and the bolsters in the correct orientation. So here's a picture of a deck being tied. So the slab, the supports are in 2472. So as I mentioned, for our deck construction, we have a couple different places that we look at it. But let's find this requirement for where our bar supports are. So 2472.3C2. So it is on our spec book page 550. Okay, and so there in our third paragraph down, on page 550, it says for interior bays on beam span bridges, place slab bolsters and upper continuous high chairs within 6 inches of the edge of beam flanges. So that's what this picture right here is showing, 6 inches. So from edge of beam flange to our supports, it has to be no more than 6 inches. Okay, and then there's, I can't remember if I have a slide to talk about the next paragraph there. But it says, use tie wires to tie down the top mat of bridge slab reinforcing to the in-place beam stirrups or shear connectors at a spacing of no greater than 5 feet as measured longitudinally along each beam. And so what that is saying is you would go along and every 5 feet you would tie the mat down to these stirrups, mat to the stirrups, mat to the stirrups. So that's what that part is. The other thing on this slide is this 3-foot or 4-foot spacing. So that is also on page 550, and there's that little table, 2472.3-1, right in the center of the spec of the page, I should say. And it says for bar size number 3 and 4, what is the maximum spacing for bolsters or continuous chairs? 3 feet. 3 feet. What about if we have bars 5, 6, and 7? 4 feet. Why might we think that it's a little bit bigger for bars 5, 6, and 7? Why can they go 4 feet? Because they're bigger, less deflection on the bars. So a 5/8 diameter, 6/8, 7/8 inch diameter, they can span a little bit further. So the contractor, obviously, it's money. If they have to put one more set of chairs out here along the whole length of the bridge, it's more money. They got to put an extra one out there. So, but be aware of that. That's nothing that's going to be in the plans. Your plans won't give you that note. That's something that you in the spec will have to remind the contractor. Hey, remember, you got to put in another bolster underneath there. Again, at this point in time, once they're to this stage, this is hard to come in and say, you forgot that. You got to shove another bolster in there. They could probably wiggle something in, but it's harder. So be working with them and say, just remind what we need for that. So this is what our continuous chairs and bolsters look like. Something like this is for the higher chairs. Got a couple of examples in the back there of some high chairs. But I want us to do a little exercise here for what is going to be the height of our high chairs for our bridge. So we have two spans. We have span 1 and span 2. We're going to look at sheets 35, 36, and 37. And I'm I guess I'm going to ask it this way. What are the longitudinal size bars? They're going to be the same in both spans. And what are the transverse bar sizes in span 1 versus span 2? So first off, who can tell me for the longitudinal bars, what size are they going to be? Let's look at first the top reinforcement on sheet 36. Longitudinal bars running along the length of the bridge. Okay, so let's look longitudinal. So the ones that are running from abutment to abutment. So longitudinal, they're running, yeah, so the bars that are running this way. Okay, so you had, so what you're actually looking at these bars. So you're looking at these bars. So what I want is these bars that are running this way. You can find them right here. Okay. So we see some guys are identifying S401. So what we're looking for is the bars that are running this direction. So they're running along the full length of the page. Okay, so who else? You guys back here got it. What bars are you seeing? So it's a bar that's going to be running from abutment to abutment. So the bars that are running here. So that's the right lap. So what's the bar? So looking for bars that are running this way. So it's going to be bars that something that indicates it. Bars. Okay, is everybody following them? So we're looking at the bars that are running the length of the page. There's these bars, they're kind of in the middle. I'm on page 36. It's an S401E. And there's a bunch of arrows running to them. And then over here, it's an S402 on the end. So what size is that bar? Number 4, meaning it's how big diameter? Half inch, 4/8 or a half inch. Did everybody see that? Okay, so now how about the transverse? So the transverse on the same, on the top reinforcement, page 36. What's the size of the transverse bars? Okay, heard 5 for span 1, 4 for span 2. Everybody seeing that? Okay, so like here is the designation,
So here.
here is the designation. And so that's showing that all of these bars going this way. Oh, okay, see that? So these bars, so these dimension lines here are saying that we start on dimensioning a bar up here. And then and this is a 4, and over here, what number is that? That's a 5. Okay, are we able to see what we got there? Okay, so the transverse are the ones that are going perpendicular. Okay, so again, span 5, or pardon me, span 1 has number 5, 5/8 bar, and span 2 has number 4s, or a 1/2 inch bar. Okay, so everybody get that? Okay, that's a key part of reading what we have on our plans. Okay, so what are we trying to do? So that means in our plan, we have different size bars. So it's 5/8 inch in span 1, and this bar is a 1/2 inch in span 2, and then the longitudinal bars are going to be 1/2 inch in each case. So I think we have some math that happens here. Yeah, what size are transverse in span 1 and what are they in span 2? And so we just put in some numbers here. So the continuous chairs that they bring out actually have to be different in span 1 to span 2. Because that the chair will sit on the top of, depending how they do it, either on top of a bar or on top of the bottom bolster. But typically it's going to be on top of this bar. And so this little arrow to this little arrow is showing that's 3 3/4 inches. Because we will go on top of the transverse bar and then we will space the longitudinals in there. And then we'll set the top transverse bar on top of then the high chair. So what this is telling us is that if they would come out there with just 4-inch high chair in both, they're not going to have the correct overall 3-inch clearance to the top of the deck. Because if they went with a 4-inch chair, that would push this up. So just be aware of that, do some math, make sure that the contractor has the correct elevation and size of things. So that's a little complicated. Any questions? Your head spinning or you understand? Anything I can help point out? So the key thing is identify what's longitudinal bar, what's transverse bar, what kind of things, how are those chairs going to be supporting the other bars. So that's what this little exercise is helping us to do. Okay, after that exercise, let's take a 5-minute stretch break, so like 21, 22 after.
No, absolutely not.
The construction. Oh, I heard you.
And I already knew that was how the exercise, but he was trying to take us, he got everyone says it's so, and I kind of self-taught some of that. I go ask a lot of questions. you know, like we're standing at the door and somebody's, they're like, "Are you again?"
Okay, let's get rolling again. So any questions on what we're
I was like,
doing
for what?
on those a few exercises?
Best thing you do is go through and highlight the plan, if you find all the bars, right?
Yeah, just find out what the bars are, what some laps are, and, you know, all that kind of stuff will help us when we're been out in the field trying to inspect. Yeah, there's just some key dimensions always and key bars. Okay, who sees anything wrong with this picture? Can we tell what's going on? There's a bottom slab bolster right here, there's a chair right here, there's a bolster over here, there's a beam over here.
I think your high chairs are going the wrong way.
High chairs are going the correct way, but yeah, they're in between those slab bolsters. So these should be stacked, so the high chairs should be right over where the lower slab or the bolsters are. So you see that that's in the wrong direction. So here, this is an old slash, if I almost take this one out, but among the things they're talking about is some of this plywood isn't matching, you know, I don't know, check what the spacing is on some of those bars, walkways, studs not placed in portions of dirt, so, but I think it's a lot of times, we want to make sure that our bolsters and our chairs are in the correct location. Here's an example of walkway provided across the rebar. Don't see this all the time, but the one thing I would say is, as inspectors, do your best not to mess up what the ironworkers have done. And that means if we can walk right along where the bolsters and the chairs are, instead of being out in the middle, you know, that's always better. Just be careful where you are walking. And yeah, just be careful out there. Continuous high chairs, so that's just a picture again showing what we have with continuous high chairs. Before the bars get put up into the deck, we want to make sure that they haven't been stored in a place that can get dirt on them. And perhaps things need to be power washed. Also, we want to check the specs. There's a spec that says you can't have them exposed to the sun more than 60 days. That includes rail bars that oftentimes they're fabricated or tied in place, and they're going to sit there for, you know, many days, many months even. So, but there are spec requirements to protect from UV. And it's a decent job here. Even you've got some kind of wood chips or something to keep the splatter of dirt, but just make sure they do a good job. We looked at that spec earlier, and I guess I do have a slide here that we want to make sure that mat doesn't float, so we have to tie it down. So that's the middle of page 550 and the 2472 portion of the spectrum. So tie that down. So what would happen, it could potentially float. If you left the mats untied and you place concrete, that even though that's a lot of weight, yet the hydrostatic pressure of concrete could float those bars up, and then all of a sudden they're out of position. So thus the requirement there. We had looked at this one too. So the high chair, the spacing of supports and the ties are for number 3 and 4 bars, 3 foot. The little bit bigger ones can go 4 foot. So be aware of that, and then the tie down is 5. Also on page 550, one of the first jobs when I was a Metro Region engineer, I went out to a site and iron worker said, hey, we don't have to tie every 100% of these top bars, right? I said, wait a minute, I think I remember the spec. And indeed there is. So there is a spec, and on page 550, it is to tie the bottom paragraph, tie the top mat of epoxy coated rebar at every transverse bar intersection along each continuous row of longitudinal bars. It leaves out the stagger bars that we're going to talk about in a little bit. That doesn't have to be tied 100%, but everything else, every longitudinal bar, where it needs a transverse bar, it gets tied 100%. And iron workers, they still like to say, well, why do I have to do so often? We're not moving. Well, that is our spec, and we want to make sure they don't. For the bottom, then, it's every 50%, every second transverse bar intersection. So those are specs that are right there in the bottom of page 550. So iron workers will often ask that question, and we wouldn't want them to. Okay, so top reinforcement. We want to look for the additional stagger bars. So this is on page 36 of our plan. There's a little stagger diagram, and so down in the bottom here is the stagger diagram. This is additional bars, so the ones that are going, the longer ones are the S401Es, but the additional bars are 15 feet long, and there's 2 of them in between each one. So there's a couple places that we see that. So that diagram, stagger diagram, shows how they're laid out. And then here, in that detail in section 8A, it shows what the spacing is. So the typical longitudinal ones are 1'6" on center, and then at 6-inch spacing is the S603 stagger bars. And so that is shown there. So those only go over the pier. It's very typical on a pre-stressed girder job. We essentially make the deck continuous even though the beams end. We're making the deck continuous, and those stagger bars help make it be continuous. So be aware of that detail.
Where in the spec does it say that you don't have to tie those 100%?
Because the spec says tie the top epoxy coated rebars at every transverse bar intersection along each continuous row of longitudinal bars. So those staggers are not continuous, they're just 15 feet long. But good question. Okay, so additional deck rebar. So we've noticed as our bridge is skewed, and at the edges of our deck, there's some additional bars. So if we look, this is showing on page 39. And so we see these extra bars, the S413E. So the S413E bars. At the bottom right of that detail, corner detail, it's 10 spaces at 6.5 inches. And then as they go up toward the expansion joint, they're getting a little closer together, and you kind of fan them to fit. And it says there's an additional note, 1.5 inches between the flared bars. 1.5 inch minimum between flared bars placed as shown. So it's not saying it has to be exactly, 1.5 inches, or it doesn't have to be exactly 2.25, but fan them as shown. What is the length difference of those series bars? What's the shortest and what's the longest of those series bars? S413. They're the 6.6, and the shortest, what's the longest? 10.9. 10.9. You see that in the chart, in the bill of reinforcement? So that's 413, that's 2 series of 11. So that means there's gonna be one on one corner and one on another corner. The shortest bars are 6'6", the longest is 10'9", and you put them in there with, you know, the 5.5 inch spacing down here, and then fan them kind of as shown. Okay, Mark had talked about this. We want to always make sure that we're picking our bars correctly. Continuity diaphragms, these are poured with the deck, don't pour ahead of the deck pour. These are bigger diaphragms that are tying everything together. And back in the day, we had tried casting this first, letting it set, and then come with the deck, where we found more cracking and stuff. And so now we just say cast it with the deck, don't pour it ahead of time, and things have worked out better. So if you ever have a situation like this, just be aware of what the requirements are. Here's some pictures of expansion joints. So use epoxy touch-up on the welds, don't bury rusted coil rods like shown here. We don't weld deck reinforcement, grind off for galvanizing, and then re-galvanize it. And all steel on the deck must be welded. Sometimes there's no workaround, and so an occasional tack weld has been allowed, but again, I'd rather have a solid expansion joint than to say, oh no, the spec says no welding rebar, and then they end up with a sloppy job on the joint. So be aware, sometimes you do need to do something, but it really has to be minimized. Also, if we're going to have a secondary pour, we want to protect epoxy, the concrete, the rebar from the concrete splash. This is more so on rail bars, not necessarily here. This is just kind of an end diaphragm. That would typically, everything would get poured with the deck, so it's not quite a big deal. But a rail rebar is more of an issue. We want to maintain the cover, including to the ties. So they'll come along and they'll tie these, and sometimes those ties don't get stepped down, and they'll tie them and it comes right up, and all of a sudden it's right up to your surface. Well, that's the exact path then for water to go down through that tie, alongside the tie, or maybe deteriorate the tie over time and get right to your rebar. So, you know, sometimes you as an inspector might be able to stop some down as you're going by, or tell the iron workers, hey, you've got to get those ties all bent down. Control joint on piers, we want to make sure that we put the V strips where they're supposed to be. These are meant to force a crack at a certain location. So we're going to come through, the deck is going to be continuously poured, but we want to have the V strip at the bottom. We want to then we'll have a saw cut, we'll talk about that here in a few slides. But we also want to make sure on the side of our deck form that we likewise have a V-strip form that is shown there. So mark the side form so it's easy to align the saw cut. We're going to come along later, so at the top of the form, put that and maybe string line it and a saw cut. We talked about this drip strip. So again, simple but functional. If water comes along the outside, it'll come to that drip strip and then it'll drop down instead of following and getting here and deteriorating that girder. Check the bar ends. So we want to make sure if they've been cut that they've been epoxy coated and everything is clear. Water does sometimes leak under the barriers, and you know it can eventually get in and deteriorate. Different type of rebar. So MnDOT has experimented with glass fiber reinforced polymer, GFRP rebars. It'll probably be the wave of the future at some point, for some situations at least. And these won't corrode, so you have that going for you. It's much I don't know about much, but it's cheaper than stainless steel. You can do both mats in the bridge deck, and you can also bend these into shapes, you know, like here, a bend shape in the rail. They're solid bars. I think there's plenty of test data that shows that they're structurally sound. And so I think it's going to be something that we will see more of as time goes on. So be aware of that. There's been some availability and detailing issues. Province of Ontario uses this material exclusively for the bridges.
Do they come pre-bent, or do they bend them with a hot air gun, or just?
They come pre-bent, and I'm not exactly sure what the process is in the fab shop. I would guess it's something to do with the heat, they bend it in the heat, because I don't think they can be cold bent. Based on the cost of the project so far, they are cheaper than stainless, slightly more expensive than epoxy, is the data that we've had on the bridges.
How about weight-wise?
Weight, even a guy like me, skinny little guy, can carry a bundle of these bars.
So I mean, do you have, is there a table for bar size and weight?
I think there is. I am not exactly sure. But yeah, but they're definitely lighter than meshes. Another comment?
How about straight to diameter size compared to steel?
I think it's comparable. So I think if you use a number 6 steel, I think it'd be a number 6 of these. I'm pretty sure. The carbon fiber it's pretty amazing. Right? I've worked with it more where we've had bridge hits, and they smash up a pre-stressed girder. And one good way to do that is they wrap it with this GFRP, and then you know the carbon it's stout, and it's really strong in tension. So I really think at some point it's going to be a product that you'll see. So if you're able to stay in the bridge industry for a number of years, hopefully there'll be something that this will extend some of the life of our bridges. So here's a picture of a couple of the ones that were done. So, but again, they're lighter, they're easy to place. I think tying is no different. Utilities, we do have a little section on utilities, but in the deck, if you have any utilities in the deck, make sure that they're in the right location. Here's something, maybe one of the traffic signal things or whatever, maybe a light pole or something in the middle of the deck. Obviously make sure that things are in the right location. Okay, so we'll transition now to how do we finish these decks? And the contractor has to understand each span has to be loaded uniformly, especially if you're on a skew. We'll talk a little bit about some of that kind of stuff. We want to have elevations correct for expansion joints, for bulkheads, for copings. As inspector, the numbers will tell us one thing, but our naked eye will tell us another, that we can sight down the rail, and if we see all of a sudden there's a little dip, well, something's wrong. That shouldn't be like that. And so oftentimes that's the final check, is just look, does it make sense? Does our naked eye check seem right? Okay, what do our specs say? So page 367 of the spec book talks about our power supported screeds and things. So let's turn to 367 and let's see what it says. Okay, so we're C-4, which starts actually on page 366. But we're going to, for this first one, we're talking about bridge deck slabs. And it says, support the screed rails for power operating screeds on the exterior beams, girders, or webs. Provide calculations if planning support on the side forms. Okay, so page 367. We also have some requirements in our special provisions. And again, we have the wrong special provisions that we handed out in the class. The right ones are now on the website. But for 2401, it says this: operate the finishing machine for our bridge so that the longitudinal axis is generally parallel to center line of bearings. So all that means is, as we start placing our concrete, and we have a skewed, our bridges like this, our abutment is skewed, we're going to keep placing our concrete essentially parallel to these substructures. This is a diagram that's in the bridge construction manual, and it just is showing kind of the differences at any of these sections, at A, A, B, B, or C, C, what the difference in deflection is if we load it differently. So not going to get into that in more detail. We also have requirements on page 364 that talk about if we have at least 2 spans, the concrete has to remain plastic for at least a 1/2 span length back, and provide admixtures as needed to retard the concrete setting time. So what does that mean in the real world, in the practical world? So let's look at a little diagram here. So if we start placing the concrete, and we're placing the deck from the abutment toward the pier, and we keep on going, it should keep going. There it goes. So we now are placing concrete into this next span. It's saying we need concrete to be plastic in that zone. So when we reach midpoint here, the concrete at midspan in the previous span must still be plastic. So what that is reminding the contractors, use admixtures or keep a fast enough placement rate so that concrete doesn't set up. The reason we do that is if the concrete sets up, it's more prone then to some tensile cracks, and you get cracks in the deck. There's also requirements then, page 363, of having a trial run with the strike-off machine. And this is something, so this is on F3C-1, very bottom of 363. And it talks about putting in checking the depth and a shim to the rebar. So again, maybe a picture will help explain that, but essentially what we're doing, we're verifying that the slab thickness is correct and that we have clearance to our rebar. So here's the first picture we've seen of a finishing machine. So the concrete gets placed up in this zone, gets vibrated, and then this is the first little auger that will help to get it to about the correct elevation. And you have these rotovibes, and then you have these cylinders that are finishing as a concrete. So a very typical type of an operation. You want to check that your roadway crowns are in the right location, and any strike off is done correctly. If you're off the bridge, you obviously don't have any deflection. You're right on the grade. And so whatever grade rails, screed rails you have, you don't have to count for deflection. But when you're on the bridge, you need to count for deflection. We also want to make sure we have clearance to our expansion joints and any bulkheads and so forth. So if there's a lot of adjustments, go back and redo it. The dry run is required 24 hours in advance. And so just make sure that they do that. There's also requirements for a pre-placement meeting, right in the spec, to do a pre-placement meeting. And that's a great time to say who's doing what, how many people are finishing, how many people are curing, how is the concrete, where are the pump trucks going to sit, and so forth. Make sure that they are aware. And so, but require that dry run 24 hours in advance and postpone if needed, especially if there's no people to make adjustments. The strike-off rails, so we'll have a couple of pictures coming up here that will show what the strike-off rails are. But they'll be supported by placing a rail system on each fascia girder. So again, sometimes they want to go on the edge of deck, but typically it's going to be on the fascia girder. And so the screed rails on the overhangs or the edge of deck, there's extra loading, and there's also a reduced area for finishing if you go on at that particular location. So the strike-off machine that travels on rails are supported by adjustable posts. The next slide will have pictures of that. And after all the rails have been set, check the vertical alignment. And this is where kind of just the eye test. Look and see if everything is consistent. And here's a picture of typically what we have. This one is on the edge of deck. This one, there's some post tensioning in here. And so that's a different kind of a bridge, and there's not even a girder that would be available to set your screed rail on. And so the formwork would have all been designed accordingly. But here it's on the overhang. Here's a finished machine. It's pretty big type of machine. Here's the screed support. So what's the problem here? It looks like this screed rail isn't even down on its support. So if you come along with the load of the screed, it would deflect down. So make sure that it looks like everything is engaged, everything is good. Plus, obviously, nowadays, all that would be coated. Sometimes our bridges get so wide that we're going to cast them in two phases. Like our bridge is pretty wide. It's nearly 100 feet wide. That maybe the contractor would have wanted to put a joint right down the center. And so this is a case where they did. They put a longitudinal joint, bulkhead, all the way down here. So this is the typical forming, and they would then cast the concrete here from here to the left. Then later they would pull out those forms, and then a later phase they would cast this right portion. So this usually wouldn't be governed in the plan, shown in the plans. I remember a bridge, Highway 100, one of the bridges there, I think it's Highway 36 over Highway 100. And the contractor actually did two different finishing machines. There was a center median, and they just went with one, and then 20 feet behind was the other one, and that worked out well. So there are different ways to do it instead of putting in a bulkhead. So a couple different types of forming. For conventional with overhang, you run the finishing machine on the fascia beam or slab span. You don't have overhang brackets. You just form everything. So here's a completed slab span of how that works. Slab span, there would be some additional language that they need to furnish false work plans. So again, in the forms and false work section, we looked at that, designed by a registered engineer, reviewed by a second, and then he or she shall conduct and sign off a field review before the concrete is placed. So that's all part of forms and false work and the things that we do. So slab span elements, we've just looked at some of these before, some of the forming for them. And this is a Hodge slab span where it gets a little thicker at the pier. So we see a pretty big hump going over there. False work, a lot of times it'll be, different girders and things like that with stringers going transversely. Some plywood shims and hardwood blocks and things. So lateral bracing, so the end of it, for a slab span, there's a lot of pressure. Again, if this is say 20 inches thick, there's a lot of concrete pressure that's trying to push that form out, and so you got some substantial bracing that's going to come down to withstand. So here's working on the forms, on those edge forms, trying to, again, not only the end, but obviously here along the length of the bridge, a lot of bracing to keep it from tipping over. Sometimes we will have a requirement to cast in a certain location first. And this is if the spans get long enough that they can't achieve and keep concrete plastic at half a span back, we would require that they do a deck placement. So all this is showing is the first one is from the abutment out to this location. So that's core number one. You're trying to get some of the positive moment reflections out. And then you're going to come, core 2 is coming this direction, and you're going to come back. That is coming over a negative moment region. So positive moment is typically mid-span, negative moment is over the piers. And we're just trying to minimize the amount of tensile forces that might happen during a deck pour. But if you have longer span, if you're on a steel bridge with longer span, this might be in the plans. So just be aware of that, of what it means. And so the sequence oftentimes would be for the spans that are greater than 200 feet. Typically we place a positive moment first. Sometimes it combines a positive with a negative moment. If we're simple spans, it'd be support to support. But this is kind of the rule of thumb. And we would maintain a pour rate of 0.6 spans per hour. So essentially a little bit less than 2 hours, you got to be able to do each span. So you got a 200-foot span, that's a long ways to go. And then you'd wait 72 hours. This last part, do the center part after 72 hours. So you can wait for concrete to cure before you do it again. So the special provisions might have things like maintain 80 cubic yards per hour. That's a little bit more, you can track that better than the 0.6 spans per hour, but whatever. Just read the special provisions, know what it is. And especially on slab spans, where they're thicker, even though the spans are less in length, it's a lot of concrete that you need to keep going. So they want to maintain 80 yards. For deck cracking, to minimize it, we really want to see what the contractor has. So sometimes we would say submit your casting procedure for approval. And if they do something different than what the plans are intending, the stool heights might change, especially, so we're taking a lot of deflection out of one, but it's restricting the deflection in another point. So it's even possible reinforcement may change. I guess I haven't seen that in my days, but it's possible if you really change something up that you could have some changes there. Here's a transverse construction joint. This looks like it must be on a skewed operation. And so essentially going across the deck rather than going just on a skew, which would be hard to form, they're going perpendicular and parallel to the bars so that you can fit your forming in So the bulkhead needs to go between the massive rebar and under the bottom mat. Because if you didn't have it under the bottom mat, then the concrete would kind of slough underneath the form. So here's some more spec stuff that we have. So there's a whole bunch of specs there, page 3, starting in 363 all the way through 376 of what the forming is. But we'll bring to your attention this one, that provide a placement and curing plan at least 14 days before the slab placement to the engineer for approval. And these are all the things that they need to consider in that placement plan. Now, what is your delivery date, rates? When are we going to start and finish? Are we starting at night, finishing in the day? Are we starting at 6 p.m. and going through the night? And whatever's going to go on. What's the material, labor, equipment for placing, finishing, curing? Including, how are you going to do your curing? We'll be talking about that after lunch of the whole curing method. A number of work bridges, people responsible, and any bulkhead that if something were to happen. You know, what if that form blows out like the couple pictures we've shown? What are you going to do? You're just going to throw your hands up in the air, or you have a plan? So the reason for this is to make sure they have a plan of how to do the whole thing. So just to look a little bit closer than at some of this, on page 365, it also requires a pre-placement meeting. And that means get the people that are going to be in charge, get the foreman, get the curing person, you know, maybe have the concrete supplier there, get the chief inspector and somebody that's doing tests, whatever. Get those folks involved and talk about some of the things in the placement and curing plan. What's the crew size, who's assigned, so forth. And as far as you guys, as inspectors, who's taking the concrete tests, who's checking the thickness of the deck, you know, whatever, all those kind of things. And then what happens if we're going to if any concrete tests fail, what are we going to do? So here's just something like, you're going to pour a deck. Okay, I'm going to pour a deck and I have 12 people coming. I got a finishing machine operator, a couple of gutter line finishers, some main line finishers. I got people knocking down concrete. I got somebody doing the vibrator, curing and placement, a couple people, and a supervisor. So is that adequate? Yeah, it looks good if it's a small deck, but if it's a big deck, maybe you need more. There is a deck placement checklist on the Bridge Office website. This is a handy tool that, as you're getting ready to cast a deck, maybe run through this and just see. Next one blows it up a little bit of, you know, when are we starting, delivery rates, manpower, so on and so forth. This doesn't have to be filled out, but it's a good tool to help remind you that these are the things that I should do. So, you know, different things here. I think it's 4 pages or something. So a lot of things that can help remind of what is needed. All right, it's noon. It's lunchtime. Any questions before we take a break? All right, so let's be back at 1.
No.
Yeah, I was talking about like going to the system for a while there. Yeah. I wasn't sure.
All right, we're gonna go on for the afternoon here. Anybody have any questions before we continue on? Okay, hearing none. So there's a few other requirements in the spec of how to place concrete and the kind of things we need to look at. I think we mentioned this one before, the no concrete shall be dropped over 4 feet. That's due to consolidation, that segregation, that you segregate the aggregate from the rest of the paste, which you do. Also this one, of all the concrete equipment and curing material should be on hand before the start of the pour. It makes sense. If you're not ready to cure, you're not going to cure adequately. So make sure that they have everything ready to go. Want to watch for any rebar that we get displaced if people are walking on them or whatever. Vibrating, we want to avoid honeycomb and segregation issues. There's also a requirement that you need to strike off the concrete within 10 feet of deposited concrete, unless it's a high skew. All that's meaning is don't go out to half the span placing concrete and then you finally get around to striking it off, because by then it'll start to harden up and you could have drying shrinkage and stuff going on in there. So pretty self-explanatory on that one. Concrete placement over traffic. This is something that's changed in the past couple of years. Be aware of your special provision. In the past, we used to routinely place deck concrete over traffic, but that has changed. So review your specs. Now, a lot of times you require them to shut the traffic down or go up and over a ramp if that's available, a little detour, whatever. So review your special provisions. If there's an absolute need, I think there's things that the resident engineer or the project engineer could get into the spec, but anyway, just be aware of what might happen. So there's 2 different types of deck floors. We've so far showed some pictures of the Bidwell finishing machine. And so a structural deck pour with a separate wearing course, meaning that there's 2 pours. Like, well, actually, I'm not going to say this question because it's coming up on a future slide. We can use a Bidwell finishing machine, or we can use what's called a Morrison screen or an air screen. And we'll show some pictures on that. So on page 366 of our spec book, so that whole 2413 F3C4 talks about strike off of bridge slab, and that's for both, but then toward the bottom of the page it says bridge structural slabs. And so that's the portion here on page 366 of what it would be. The structural slabs can have a little more variation because we're going to come along with a separate wearing course and level everything off. So I also want to turn our attention to the spec on page 368 of what our variation is. So right kind of in the middle of the page, it says produce a final surface including areas near expansion, diameter, such and such. And number 3 there, does not vary by greater than 3/8 inch on a bridge structural slab. So that's the first part up here. So again, a structural slab is going to have a separate wearing course. If it's full depth, or we've used the word monolithic before, you can only use a Bidwell with an auger and a cylindrical finishing machine permitted, and less complicated geometry. And that there you might need to use the air screen. But that again is on page, actually that looks like This is a typo, this should be page 367, the bid well. It's only for the bridge deck slabs, bridge without a separate concrete wearing. Of course, so that's page 367. So apologize for that. 367 is that page. And then the surface tolerance here, it shows up in a couple of different places, but back to that page 368 where we looked before. Item 4 shows does not vary by greater than an 1/8 inch. And so I checked with the 10-foot straight edge for bridge deck slabs. So we see the difference there. The surface tolerance, if you are running on that surface, a full depth deck pour, we need to be a little tighter tolerance. So if we were going to do this deck without a separate wearing course, what would be some of it? So this is our bridge deck. Without a separate wearing course, what are a couple of the challenges that we might face? So if we needed to come along and do a full depth deck,
Medium width.
the median, what's the median doing? One side or the other, it's kind of varying all over. So to set up a finishing machine, you'd have to contend with that. You'd have bars that are projecting up out of the deck, so you'd have to somehow hop up and over, or maybe you'd set up one machine on this side and another on this side. So that's not too conducive to doing a full depth deck pour. Now, if that median was straight, maybe that'd be a little easier. Then maybe we could do half of it with one finishing machine, another one with the other. So, that's something we would see. Also, we have the trail areas. How are those going to be finished? So we have bars that are extending out. So there's some things we need to think about as to the type of deck pour and the type of geometry and things like that we have. So here is called a Morrison screed or an air screed. So it's a little triangular thing like this. It has little motors with like offset cams that it's kind of vibrating that whole screed. And I'll show pictures that sometimes they ride on little feet that ride on the rebar. And in this case, it looks like this is for a thicker deck, 3 inches of cover. So this is a full depth, and they're riding it on screed rails. And so that's something you might run into. It would look like that. More typical would be this situation where right here and right here and right here are these little skis that the machine is riding on skis, or the machine has these skis that ride on the rebar. And so that machine is actually riding on the rebar, so it's important that the rebar be in the correct location. It does maybe scuff that a little bit, but it's not a lot of weight, but it is some friction coming across. We haven't noticed that it's been an issue that, all of a sudden there's a line of corrosion right where that's riding. But you're right, it probably is at least scuffing it, but maybe it's not cutting all the way through that epoxy. But yeah, we do allow it, and it's very common, especially on these structural slabs that just have 1 inch of cover then from the top bar. There's always little joints in these things, so you can adjust them at the crown break. But as they're running them, they need to do that. The spec says it has to be, what's the word it uses, self-propelled or something, that it has to, self-propelled is for the bridge deck slab, but it has to be a power. You can't just pull it. It has to come with a little winch cable. And so this little motor is attached to a winch cable. somewhere, I can't see it where I'm at, but at any rate, that'll pull the whole thing forward. And then these are some of the connections to make for the crown breaks. And so here's, you can see some of the bar that it runs on. Typically, it would be running, across the transverse bars. It looks like, I don't know if this is the way this is run or this is just the way this thing the picture was taken. But here it's sitting on the bottom of the two bars on the top mat. So typical operation, so they deposit the concrete, there's somebody with the vibrator, other people raking it to kind of get it to close to the right elevation, and then the Morrison screed, again, it's vibrating, and so it's able to get a smooth surface. So very typical process. We also might need that on areas like this. So even if we were doing, say, a main line, and say we had a regular finishing machine over here, in this gore area, we might need to have the Morrison screed. Another lesson learned. Sometimes we have real deep girders. And this particular girder is 82-inch web. So we have, say, a 7-foot deep girder. The thing is this tall. This is the deflection diagram for this girder. The abutment was over here. The deck pour started here. Just a little bit of, actually, I take that back. The pour started here. And they went toward the center. And there's a lot of deflection in this zone. But we will, I might ask a question of what you think might happen. But deep steel girders deflect, which causes rotation of the ends of the girders under the expansion joint. So we can imagine what's happening. So we've got a big deep girder, and this thing deflects down, that end doesn't stay, but the whole thing acts like this. So it goes down, and so we can imagine that deep girder, 7 feet, if you have, even though if we're out, whatever this was, a couple hundred feet, 111, 50, yeah, so we're getting close to 200 feet, whatever it is up here, 200 something feet. If our deflection was 5 inches, it's going to cause a rotation of that girder end. So this is what happens. Deflection was 5 inches due to weight of concrete. They started at the abutment and they went to the right. By the time you get out to mid-span, you got most of that deflection is already coming out, meaning that girder end is moving. So what's happening here is going to be how that end is formed. I'll have a couple of diagrams that will show that. But what they noticed out there is cracking right along in the end block. Right, you can see here the cracking. You see my keys as a reference. But all this cracking, that means that something is going wrong. You go down below, this is what some of the forming looked like. Is forming at one point was attached to the abutment, which isn't moving. But then there's other stuff that was forming up for the deck, and it's trying to move as that end girder is deflecting. So the end block forming was supported on the girders. And to use this diagram in this picture, depending how you form this end of girder is moving to the right. So this from right here, it's moving to the right due to deflection that's happening out in the mid-span. The forming for this end block was actually attached to the girder. And so this little piece of concrete that's, say, at the shear, it says, I'm fine staying right here to my buddy, the pyramid. But its neighboring concrete that's right here is saying, well, I'm going to go with my forming that's over here. So all of a sudden, you got concrete that's separating right here. And so the crack was forming right up in this zone. So the first time I noticed this was on Highway 100. And after that, I tried to make sure that I was telling the people out in the field to watch this issue. And on 35, unbelievably 35E, I told those guys, watch this issue, and sure enough, the same thing happened. There was a couple of contractors in in this class 2-3 years ago, and they finally said, oh yeah, that's it. And a couple of them had formed these exactly the wrong way. So I pointed out to you guys that these are the kind of things, think about what's moving and what's happening in deflection. So what should we do? We should keep the end block support separate from the deck support. To allow the joint to open during rotation and always think about what is moving. So I got a couple little blocks that'll come in here, so the better way to do it would be to have some kind of a blocking that's on the abutment. This end block isn't moving anywhere, and so all of the forming should be there. And then for the deck itself and the thickened end block, that should be formed to the girder. Where what they had done is form everything from the girder back to this portion of the end block, thus causing.
Would it make a difference if you poured the end block separately from the?
Yes, so that is one other thing we could do. And it's right here. So another option, Linda, you're going to be able to come teach this class. That's very good, very observant. But another option would be to cast the end block after all the deflection was gone from the span. So in this case, it was long enough span that they had a pump here at the abutment for the first part, and then another pump once they got out to mid-span or wherever. So one option would be cast this concrete as far as you can reach. Most of your deflection is gone. This joint would have opened up, and then come back in and cast the end block. For this case, with that crack that happened, they had to tear out that end block. They had to, re-put bars in there, and probably damage some of the anchorages for our joint, and so forth. So that's how they repaired it. But yeah, either form it correctly or cast that end block last before you move to the other side of the bridge. So kind of a lesson learned. Just think about what's happening out there during some of these things. So this is a conventional finishing machine. We can see the workers there, some guys with shovels, some with vibrators, and you don't want to mound up too much concrete there, but you want it to be just enough so that the finishing machine can finish it, and so forth. And we'll have a couple other pictures here as well of the other finishing operations. But in this case, that finishing machine obviously can only come to these bars. It doesn't lift up and over and then do this. And so this is all a separate, done by hand methods. This was on St. Croix. We had just a ton of pictures, and where this picture was taken, they used to take a picture on the hour to the west, on the 15 minutes to the north, and so anyway, every 15 minutes you get a picture going one direction or another. So, and this is just showing one of the operations of casting the deck. This is a cast-in-place box girder, but you can see a lot of people are needed. Pump truck down here, people finishing concrete and vibrating and so forth. Conveyor belts are still sometimes used. There was Red Wing Bridge, I believe, was maybe one of the last ones, but sometimes when it's hard to get pump placement, they can still use conveyor belts, and it goes out through a series of conveyors, and then it can be placed. So this obviously is a very old picture, but can still be done. 4-foot max height of the concrete fall. Also a vertical orientation of the vibrator. We don't want to be moving the concrete. Sometimes the workers get lazy and they put their vibrator in kind of horizontally in order to, then this guy can just keep placing concrete there, and he's using a vibrator to move it. Well, that's not how we would want to do it. Concrete testing. So at the start of the pour, we need to test. But the priming the pump does create a slurry, and we want to discharge some of that so the slurry isn't what we're testing. We're actually testing the concrete. So just make sure you discharge a little bit before we would do our tests. I mean, you'd hate to do a test that's somehow affected by the slurry, and then we go in and change the whatever in the mix, and all of a sudden now our slump is way off, and you can have all kinds of issues. So have the contractor tell you when the concrete's ready for testing. And so, but you need to test, early on. We don't want to get too far down the road. But testing too soon, again, if that slurry is affecting your test, then all of a sudden you might start rejecting a truck that shouldn't have to be rejected, or adjustments, and then overcompensating and things like that. For surface finishing of the deck, so page 367 of the spec book has some of these things that don't overfinish. No use of steel trowels, float only enough to close the void. So any of you who have been around concrete, whether it's sidewalks or your own construction, you know that you finish it too much, it brings bleed water up, and then you start finishing bleed water in, and it can be a problem. It does require a 10-foot highway straight edge, which is instead of modified, I should say highway straight edge, sometimes called a float, but it's required behind. We just want to get all those imperfections out, get it as smooth as it can, and we also want to make sure our crown is in the right location. And then there's a requirement to texture the surface with a carpet drag, or they could use a broom type finish if needed. So that's on page 368, final finish texture. This part here at the bottom, one, texture the surface by use of carpet drag, heavy brooming, and or tining.
Why are they still tying bridge decks?
Tining?
Yeah,
That's for skid resistance.
these are really loud.
It makes them loud. We'll talk here about, we did some noise studies that if it's true perpendicular to the roadway, it's louder, but if you put it at a diagonal, the right tire is going over at a different time than the left tire, and it's...
Like a 10-degree skew or something?
Yeah, exactly, and so that makes it better. But, yeah, in the metro, most everything nowadays is getting plain because of noise issues. There was some, I don't know, it was about 15 years ago, there was actually legislation that was passed to prohibit concrete pavements in the metro. And they were going to do just bituminous because of the noise. And then that didn't fly very well, and even some of the, like 394, where I used to drive a lot, they put a bituminous wear course on there instead of right over the concrete pavement. And then a while later, that was starting to fall apart, so they went back and they just did a planing of all of the roadway to do that. But it was all as a result of the noise. So, but we still do tying bridge decks, rural, that's the vast majority of it. Maintain the rate of pour, and we'll talk about curing now. We haven't talked about curing, but we want to place wet burlap within 30 minutes. This is a picture just to show if you don't properly consolidate and properly finish it up, you get a lot of air holes, bug holes, and things like that. So it's important to finish as we need. Here's another one. This is probably drying shrinkage. If wet cure was not put on there properly, and we know that this is just going to cause a lot of issues of chlorides getting down to the rebar a lot faster. So that is not good. We want to avoid that. So here is the 10-foot modified straight edge, or the highway straight edge. We see a tooled joint. that gets put in. Work bridge, this can be used for like the guy that's up there running the straight edge. Also then a work bridge is needed for the wet burlap and things like that. So it's a real typical, the finishing machine we can see in the background back there. So again, deposit the concrete, vibrate it, finish it, and then you have some of these additional things that are going on. Surface finishing for structural slabs, it's not so critical because we are going to come with a wearing course. The big thing we want is we want that there will be bond, so there's going to be enough texture, and then we'll have a bonding grout, which that's a different discussion for the wearing course we'll get to later this week. But here we see instead of somebody with an actual broom, they're actually pulling it. They got a broom on some ropes, and one guy here, another guy on the other side, and pulling it back and forth to put the texture in. We're not concerned that they're marring the surface when there's going to be an overlay on it, but if it's the finished surface, we are more concerned about that. So there's a couple different, and that's again why we talked about the definition early on. So surface finishing with our straight edge and our tool joints. We do need to be within the tolerance. So we looked at the specs there, either an 1/8 inch or 3/8 of an inch and 10. This looks like it's living up there, whatever that number is. It looks like 1 inch is here. So yeah, if that's a structural slab, they're maybe okay. If it's a finished one, it looks like it's a little bit much. So the surface also has a texture. Even though we're going to come along later and diamond grind it, or if we're going to tine it, we still want to have some texture that will be put in. So the tining, there's some requirements for the tining. It shall not extend into the area within 1 foot of the curves. And so this is for drainage. And we can imagine the drainages go better on a smoother surface. Also, if there's tines in that gutter line, there would be more salts and chlorides and stuff that would get caught up in those tines. And so it could lead to earlier deterioration. Thus, the requirement to leave 12 inches or 1 foot when we are tining. If we are planing, we can only get within about 20 inches. So in that, it's a little bit different. The concrete planing goes within 20 inches, strictly because of the equipment limitations. So watch your special provisions for that. Planing sometimes is called diamond texture grinding. We'll see some pictures here that show about that. So here's some straight edge language, looking for what is the surface tolerance. Do we have any big holidays and so forth? So if we do a straight edge here, there's a rolling straight edge that can be used on longer bridges. Otherwise, the bridge construction manual suggests a couple of passes per lane, and also check the gutter line. So you can look at that information, but it is a requirement to check with the 10-foot straight edge, the kind of things, the kind of surface that we have. So here's something that looks for how accurately and how smooth that was cast. The ride tolerance needs to be met before planing. So we don't want to use planing as a way to cover up all of the errors that we have. But we also require the surface texture that even after planing, if something in an area was low, we'd still have some kind of a texture that is on there. That's the reason for doing the carpet drag or grooming beforehand. You also need to watch out on your joints. So here we're planing over the joints, and in some cases, the surface finish before planing is so bad, they end up grinding into the joints. I think the next one maybe shows it a little bit more. Here, even though we set the joint 3/4 inches low, it was such a hump in the concrete that we actually were grinding across the joints. So not desirable, and also there were areas left unplaned because this was all low. So you can see that maybe this area was planed and there's no planing, and then it hit again. But just really a hodgepodge. And also just looking here, you can see that they've ground quite a bit there, just looking at the width that's in that on the right side. So that's the reason that we need the ride before we plane. Those machines are pretty big, and a lot of you have probably seen some of the roadway mills. So these are similar with big drums with big steel spikes on them for grinding. And so this is a picture, and it's really a loud operation. And here they go across the joint. And especially, if you're right at a 90 degree, they probably put some kind of a plate or something to keep the wheel of this from dropping down into the joint. And going across the joint, see some of the. Okay, so tining still is a part of the spec. Here's on page 368, talks about tining, and that's toward the bottom of the spec, and it does require, it says install the transverse texturing or tining on a slight diagonal at an angle of approximately 10 degrees, the perpendicular from the center. And so that's been a spec add. This used to be a special provision we included, but now it's right in the spec book. And so it's a variable spacing to give a depth. See, what does it say there? Obtain randomized grooves from 1/8 inch to 5/16 inch deep. Variable spacing between 5/8 to 1 inch. And so, that's what these tying rates are. Obviously, it depends on how cured that concrete is. That, is it going to go in pretty easily, or you got to put a little pressure? And that's where, and you as the inspector too, if they're barely scratching the surface, it's going to wear off under the wheel load. So make sure it's deep enough to be functional. Curing, extremely important. And we cannot stress enough the need for proper cure. It requires a curing plan. We talked about some of that language before, that they need to have a placement and curing plan 14 days prior. Must be a surface moist condition. If it's allowed to dry out, don't give credit for that. And use the curing form to document what kind of strength that you gained. So we looked again at some of this more for the placement, but here specifically for the curing. It says submit a separate, and this is on page 375 of the spec book, so submit a separate curing plan for the bridge deck. And so what's the curing method to be used? How about the quality control names? Who's responsible for the contract? How are you going to keep temps at least 40 degrees? So if you've got cold weather concrete, make sure that's done, including the cold weather plan. But so all those things are part of the spec requirements on page 375, and that is under G.3, curing plan. And to further, so starting on page 370 is concrete curing and protection. 2401.3G. So all of this is under that section, so it's quite a few pages. So 14 days, we've looked at some of this. Delivery, start and finish, torque bridges, bulkheading, and then the 2 to 4 days ahead of pre-placement meeting. So all that again is part of the requirements on page 375. When I started in the metro region in my job as a construction engineer, we did that Lexington Avenue Bridge. Somebody mentioned it before. But it's 35E over the Mississippi River. And I still remember going out to that project, and it looked almost like this. They were this far from the end, and they ran out of short on concrete. And as they ran short of concrete, there was no cure. It looked exactly like this, and 200 feet or whatever of core. And so I asked the inspector, are they going to have any cure? So we went together and asked the workers, and when are you going to put the wet cure on? And the literal answer was, can't you see I'm eating my lunch? And things have changed remarkably since then. But because of that, and because of that particular bridge even, that has a lot of cracking underneath, transverse cracking, extensive, partly due to the lack of cure. We changed our curing spec. We require it within 30 minutes. And so, yes, old picture, but this is how it used to be done. And once they finally got around to it, this concrete was already drying and so forth. So that's no longer what we allow.
Question.
Yep.
30 minutes of what?
30 minutes of, so let's read it in the spec. here
Said strike out.
Of when you finish, it's actually when you
That's
finish
negotiable.
the concrete. Now that's, let's see where that particular spec is. For the wet curing. Wet curing method. It says 30 minutes somewhere. I just gotta find it. Okay, page 379. So 379 underneath, kind of middle of the page underneath that table 240134, bullet item 2, place the wet curing within 30 minutes after final strike off of the concrete surface. So that means they can place it, and then they vibrate it, and they come along with their finishing machine. That's the final finishing, final strike off, and then the 30 minutes starts.
So like after the drag?
After what?
After the drag?
No, what I would say is before the drag. The drag is not, that's not final strike off. Final strike off is you're running that finishing machine back and forth. So, but are you saying the final drag would be like the carpet drag?
Yeah.
No, I would say it's when they're actually striking it. It has been the intent.
Most likely they would probably drag the carpet before they burlap it, but it's still 30 minutes after the strike off, right?
That's what, the spec says the strike off. So to me, the strike off is the machine's going back and forth. That's the strike off. We got the concrete expert in here too, but.
Well, the way that I've heard, this is difficult. I'm Jacob Gave, assistant concrete engineer. And the reason why that's in there is because of what Paul was showing before. And it's pretty challenging actually to where's 30 minutes from, because you're constantly moving. And so what I've seen people do is just on the side of the forms, they write the time when that bid well is there or whatever they're using to strike the deck off. And you really only employ it if you're having a problem with the contractor getting the cure down in time. So when you say, well, it's within 30 minutes, it's more of like, hey, I'm going to implement this because, we're we're kind of lagging on getting our
'cause
cure
you're
done in a
out.
timely
You know,
manner.
if they're 34 minutes, I don't think anybody's gonna say, oh, I'm gonna dock you.
Yeah,
But to me, the intent has always been, it's the strike-off machine. It's not the time the guy comes with.
So it's strike off, cover, so it's strike off, cover, pull, drag, cover.
no.
Is that what you're
No.
getting?
No.
It's strike off and then they'll do some like mine work. They might run the 10-foot straight edge.
Yeah.
After that, and then you'll have the cure bridge behind it
Yeah,
where they're laying down the burlap. And so there's a gap where it's open. So you're basically saying where the bidwell is and where the cure bridge is, you don't want that cure bridge to be more than 30 minutes behind the bidwell.
Yeah, so again, sometimes just, especially get wider placements, that's difficult. But the intent is, it's gonna be a lot better than
You
that.
could narrow it down some more in the spec book, I think.
Well, it's more difficult than you think. We've had ongoing discussions on how to maybe improve this spec, but it's more of so that the cure gets down in a timely manner. We just don't want the concrete to be exposed sitting out there.
Yeah, so the important thing is, you know, let's get it on. So, well, that's a good point. You know, the specs, oftentimes they're that way. They're, you know, contract reads it one way, we read it another way. But what we don't want to see is that you get the whole thing done and then you come with the cure. Okay, so what about the time, the general time? So general recuring is in this table, 2401, 3-2. And so let's just look at that table. It is on page 372. We have looked at that before. What is the required minimum curing period for a bridge slab? Minimum curing period for a bridge slab.
7 days.
7 calendar days. So that means keep the curing on for 7 calendar days. So you see it down there. So that is on page 372. There's also some requirements there for the bridge slab. We see for kind of that squiggly little thing, we see 2413 G6E, the bottom one down, way down at the bottom, protection from premature loading for special loading. So always be looking, is there something also, even though the cure is something, is there something that we are need to discuss about the load? And similar for the traffic barrier, there's 45 minimum strength to apply loads, 45, but then there's the railroad tracks. And that one says achieve 4,000 PSI prior to using a traffic barrier. So, you know, this is kind of getting away from the deck, but it's a superstructure element. And even though we need a cure for 45%, if we're going to use it as a traffic barrier, so we're ready to put traffic on there, it has to achieve 4,000 PSI. Okay, so we'll talk a little bit more about what our pre-wetted, or what's our wet cure. So conventional wet curing consists of pre-wetted burlap covered with white plastic sheeting and keep that slab continuously wet for at least 7 days. And so here, wet curing shall be placed no later than 2 minutes after the finishing machine has completed the final strike off of the concrete surface. So that's a little different than our words we just read in the spec book. Where we just say now place wet curing within 30 minutes after final strike off of the concrete surface. So here, this adds, what this language does, it says after the finishing machine as complete final strikeout, but that's not how spec language is, so I think we do need to be cognizant of that.
Yeah, isn't this a wordage from the special? It says replace that special provision.
It could be. I'll have to look, because unfortunately our special provisions are wrong that we got handed out here. But it might be there, so be looking at that, at your special provisions.
Excuse me?
Yep.
On the question when I said, conventional, this is a pre-weather, you know, I wonder if that refers to like cold weather season. Yeah, probably for like 7 days, is that what you're trying to?
No, this is any deck. Any deck. So now, so there'd be multiple ways we keep concrete wet. You could have somebody with a hose spraying it for 7 days. But obviously that's labor intensive. So another way is let's just put something that's wet and gonna stay wet. So that when, the way concrete cures is it uses moisture. And if it doesn't have moisture, it's gonna start to dry out and you'll get drying shrinkage. And so this is not only for cold weather, this is any time. And so, you know, that's where, so again, this is on page 379 of our spec. Use conventional wet curing consisting of pre-wetted burlap covered for 3751 with 6 mil white plastic sheet. Okay, so 377 going on all the way to page 380 talks about that stuff. So like Jake was saying, you know, sometimes it's easiest just to write on our side form somewhere, okay, the finishing machine passed at you know 148, and you know make a notation, and then we want to have the wet cure on accordingly. So we see here, you know, they're not that far behind. Here's the Morrison screed, and they're ready here with the wet cure. One other thing I should say, this is a picture that this has to be pre-wetted. As we first started doing this, the contractor said, okay, well, I'll just throw this burlap in the tank for 5 minutes and it's good to go. It came out looking like a zebra. You start unrolling it, and this doesn't accept water super fast. And so it was, you know, some places wet, some places dry. Well, if it's dry, it's going to just suck moisture out of the concrete. It's going to do the opposite of what it should be. So wet cure for 7 days. So here we see a picture of the white plastic sheeting. This is a good job of coming up and over the rail and so forth. So, you know, keep in mind how they do that. So there are some, our table 2413-4 on page 379 has some different things for the method of curing. And depending if we're like a finished sidewalk or trail, that one, so it's toward the bottom of that table, says conventional wet curing after applying transverse broom finish, AMS curing compound after wet cure period. So it gives some different things that can be done. So be aware of that. A lot of it depends on, are we going to mar the surface? So if you have a sidewalk, you don't want to have a whole bunch of, you know, marred areas where the burlap has been dragged across and so forth. The new special provisions have a monetary deduction. So be aware of that if they don't get it on the wet cure, there's a certain restriction. And so here is what it says. Failure to place wet curing within 30 minutes will constitute the Department monetary deduction. And so that's giving some teeth to this part of the spec. Okay, so I mentioned this table 3-4. So depending on what we have, a bridge structural slab, that's the one that has an overlay. So the final surface has a low sump wearing course. Required curing method, conventional wet curing after the carpentry. What about if we have bridge deck slab? That's a monolithic. Well, what do we have for wearing surface? Epoxy chip seal, texture, sidewalk. And so there's different things we have here of how they work. So pay attention to that. Pay attention to the sidewalk. So in these tables, for sidewalk, what type of curing method can we use? This is table 3-3, and then table 3-4. We've talked about that a little bit, but here are some options. So no, you can't, a special surface finish isn't required, sorry. But you could use AMS, you couldn't use this type 1D. You could use curing blanket, you could use wet curing. Formed is not applicable, and neither is SSF2. Just how do you use that chart? For our bridge deck, which of these options is going to use, be applicable? For our bridge 27138, what kind of a deck do we have? With an overlay, and then which of these? Bridge structural slab or bridge deck slab? Bridge structural slab, very good. So we're in the top line, we have low slump concrete wearing, and so we would have conventional wet curing after the carpet wearing. And so that is what we... So newly placed concrete has to be protected against rapid freezing, vibrations, things like that. The curing time for decks will start after the concrete has been placed and continue without interruption for 7 days. So we don't take a break. With the exception of sometimes the rail bars can be starting to be tied if you keep the wet cure going. So we do need to know when the required minimum strength has been met. And so how are you going to do that? We want to protect it against premature loading, but we're going to have to check either with our cylinders or with the other maturity methods to find this out. So if control cylinders are used, make sure they're cast and covered. Place them not in some beautiful curing, but you place under the curing protection on the deck. It doesn't do us any good if we're curing the cylinders in a tank at 72 degrees and our deck is 45 degrees and struggling. So just make sure that that is done correctly. And check, we need 100%, but we also need to wet cure for that full duration. So don't let the contractor say, I've achieved strength, I can quit my curing after 4.5 days. No, it's still 7 days. Cold weather protection is something that we need to be aware of. And so this is just talking about what we need, but we need to provide, down at the bottom here, maintain minimum concrete temps of 60 to 120 throughout the curing period. So they have to provide a plan and show what kind of things they're going to do. If housing is used, we want to make sure it's vented. We don't want a buildup of carbon monoxide. So there's some spec language here in it's page 380 of the spec book. So that's talking about 3G6C, bridge superstructure protection against cold weather, and it's talking about some of these kind of things. And you need to have sufficient housing in place. It also requires embedded sensors for bridge slabs. And they shouldn't just be where we anticipate the concrete's going to be the warmest. but we should put a sensor like out in the overhang where it's gonna likely cool off the fastest. So here's some pictures of what that can look like, pretty decent system. Here looks like they put some boards on the bottom flanges, maybe some plywood. They put some heaters running through there, some tarps on the overhangs. A pretty good job there. On top, curing blankets with some movement ability for air to move through. They got some, whatever, little sawhorses or something. We also like to see something wrapped up over bars so that all the heat doesn't escape out the side. So, yeah, where's the curing on the edge of the deck? So we want to make sure that we keep that. Bridge deck cracking has been an issue over years. We now have some fibers. I have a couple of slides. I think Jake probably has a couple of slides about fibers. But this is not uncommon. And this is what the Lexington Avenue Bridge looked like after we did the no cure there. And we want to minimize that. Thus the reason for curing. And so our bridge deck cracking is oftentimes due to some of these drying shrinkage. It's the wet cure that get put on in time. Maybe it's due to the mix. And so we do endeavor, we try to have low cement concrete. We endeavor to have low water content, larger aggregates. But then there's a chart that's included in the next page. Actually is going to show what we have, and it's on page 378 of the spec book. This is in the spec book, and it tells you deck pours should only be permitted when the evaporation rate is less than 0.2 pounds per square foot per hour. And that's per the high performance special revision. And so this just shows how this chart gets done. So if you're pouring and it's 75 degrees, so the example is shown right here, 75 degrees, and the humidity is 50%, so then you go over, and then the concrete temperature is 80 degrees, so then you go down to the wind velocity is 10 miles an hour, and you get, in this case, around 0.15. So that's how we use that. You're less than 0.2, so you're good to go. If you don't get that, if you're up above 0.2, well, then you need to do some things like wind velocity. Maybe you need to put some wind screens up, or maybe you need to wait till the air temperature has cooled off, or the concrete temperature can be reduced with ice or something. Bridge deck cracking, often it's the temperature differentials that make a difference. And these are good practices. Low heat of hydration, nighttime placement has worked well. We don't require that, but sometimes the contractors say, well, that's where I want to do it. And the first 48 hours are probably the biggest. And especially if temps are low, you might want to close and add heat. To reduce the early strain in the slab, we can do things like this. Maintain the minimum rate of pour, use retarders, use fogging and wet burlap to prevent drying shrinkage. Again, this is a huge tool in our toolbox to be able to do. And then you can also look at how do we cast our spans, where do we bulkhead, try to get that negative moment and tension in the deck. So full depth, these are some additional things we can talk about. They're good mixes, low permeability. There's less late season issues because low slump has some cutoff dates. You don't have the same cutoff dates with our full depth high performance concretes. But we do need a good finish, and we absolutely need good cure. So the full depth, so here's just one. It's contractor mix design nowadays, And they have, essentially it's proprietary, you're not supposed to share these with the other, the next concrete supplier, but they all have their own, they've done testing on it and so forth, so that's all something that's well and good. They have, their percentages of fly ash, slag, other supplementary products. So I think Jake's going to talk about that again. But when it turns out good, it can really be good. If it turns out bad and ugly, it can really be bad and ugly. So again, a lot of it's the placement, a lot of it's the cure. Just make sure that we are aware of what we're doing. Fibers do get added. So here's what we have. Since 2014, we are requiring fibers, so high performance concrete requires fibers, and here's just some pictures of it. You can sometimes get some of these balling issues that happen. So be aware of that. Here's a whole bunch of the fiber balls that are down there. Additional slump is permitted.
Hey, Paul, can I just point out?
Yep.
That picture is from like one of the very first decks that we did with the fibers in it, so we did see obviously all that clumping. You generally don't see that anymore. So
And partly it's how they put it in, right? Were these put in just in bags dumped into the truck?
probably.
Yeah. And
Yep.
so if they can disperse it more uniformly, it's something that,
The other thing is this version had a higher content of microfibers than we have right now. And those microfibers, they basically nest everything together at those higher contents that we were using for this deck.
yeah, okay. Yeah, so that's good. Same thing, when we first did some silica fume, we had similar things like this, and there'd be clumps of silica fume balls in the decks.
So the Peter Randy one.
So I think there's a picture coming up here, but, oh, yeah, maybe right here even. They try to catch it on these grates and try to, just make sure you get it before it goes. But then also just, I think, well dispersed, well mixed.
And I'll get into that.
Yeah. And so without fibers, we can get a lot of cracking like this. With fibers, it actually looks a lot better. And so it's been a pretty positive experience, I think, in using the fibers. I think I'm going to keep going to finish. I'm running just a little bit beyond I wanted to finish here about now, but a few more slides. We keep going. Deck crack sealing. There is requirements in the spec book now for sealing. The contractor is responsible for sealing cracks in the deck. And it refers to some things in 2433 in the spec book. And that includes how to define low density or high density crack. If it's low density, we can use this chase method, which is essentially use a ketchup bottle to seal the cracks. If it's higher density, we flood it. So it pre-fills, or we have to pre-fill some of the larger cracks. So the flood method is something that looks like over here. The chase method would be something that looks like following the crack. And the deck, start approach panel, we want to run a string line and make sure we have a straight line. So just a picture to remind about that. Heavy loads, outriggers, we want to make sure we're fully, we have our full capacity of our concrete, our full strength. But we also, if they have a high load that they want to put on the deck, make sure that an engineer has looked at that and analyzed it. Spec 1513, page 45 of our spec book, has restrictions on how big the stockpiles can be. This was in place at the 35W collapse, but it's been strengthened a little bit based on the amount of materials that were on that deck. So just be aware of that. Deck placement video we're going to get to after, and I guess that's it. So any questions on that part? I'm glad I didn't stop 2 minutes ago. Remember how many slides I had left. But any questions on what I've covered here?
Where was that monetary part about, for the curing, or the delay in curing?
Yeah, so there is a special provision now for that.
What was the special provision?
Yeah, but I think there was something in the spec book too. Yeah, I'll find that here and break. Any other questions? Okay, let's take a break until 20 after.
Just this.
So it'd be, so it'd be, you wouldn't have to worry about, wouldn't have to worry about, just like a regular ready-mix test. You just wouldn't have a fight with it.
Yeah, that's true. Yeah, I hadn't thought of that.
If it was, we did test it.
Right.
But.
Yeah, that is,
That's all just for everybody else. They do change it.
yeah, I knew that was coming. Say, Jake, is all the testing now right out the truck? Yeah, so then, I was explaining about the slurry, then you want to pump some, use a pump before you take the test. But now,
You wouldn't have to worry about rules. Right, but his reference was to where you would take your test in conjunction with the slurry, or the best taking out the equation, because you're taking three pumps. Free pump.
Yeah, it's page 3.
So the special provision, just strengthen
So that they let them use it, let me understand that.
I understand it, it's but it's really more just having a tool.
When we first started, so 20 years ago, we started pushing more, it's 30 minutes. So taking our course. They've gotten so good.
The one thing we do have to have in the spare. They had so many there, so we don't want to put a kid out
Both trucks, sometimes mess with it.
But it comes back.
Yeah.
It's proven now that it comes back. Oklahoma State ran it really good, and so we'll come back. That probably is the big idea.
It's already in some. And you just prove it again. Why not just say